In this lecture, we're going to talk about designing an augmented reality. So not a virtual reality, but an augmented reality. So the whole point is that we need to start thinking about how to translate and transfer our knowledge from designing for virtual reality. How does it actually translate to augmented reality? There's a lot of things that are in common between AR and VR. And so in this lecture, I assume that you know about VR. So my previous lectures on VR design. And we can then focus on what's really different and special with augmented reality. So we're going to have a case study here as well. So our case study is done in Unity. It's actually it was an independent study that I did with my student, who is now a PhD student with me, Shweta Rajaram. And we explored an AR, education-based simulation, Kepler's law of planetary motion, and we actually visualized all three laws, and we're doing it with marker-based AR. So here on paper, you don't really see it exactly, but the paper functions as a marker. It also has information about the law, and we're using it in very interesting ways. So it's really a nice, I think in my opinion, it's a nice use of marker-based AR. It's designed for tabletop scale, and we also have a marker-less version of it. So now I'm going to give you a quick overview of each of the projects, showing you some of the interactions that we have implemented. So in our case study, we're going to learn about marker-based design with Vuforia. Here you see all three laws. This is the first law on paper. And then you're using a smartphone. So we have essentially you're holding the phone above the paper, and then you can interact with paper, just like we did switch to a different law here. And you can also then manipulate some of the parameters for each of the laws through the smartphone. So you actually have an interface on the smartphone. What I'm showing right now is actually what you see on the screen. You can tap the simulation to pause it, for example, and then you can tap again to continue playing it. Keep in mind that the user is holding the phone above the paper and using the paper as a marker. And what is fascinating about marker-based AR is actually how you have control, very easy control over where the AR experience takes place, the scale of the AR experience, depending on how large you print the marker and how you design for the markers. And it can actually be really cool. Like you can see how these planets are now floating on paper. And I'm analyzing a little bit some of the alignment issues we have with paper, but that's fine. I mean, it is a still relatively robust marker tracking solution, Vuforia, that we're using here, and it works actually quite nicely. So we are also going to learn about a markerless AR version using AR Foundation. In the project, interestingly, we started with this version first, but the way we're going to learn about AR in this course is through looking at marker-based first and then markerless AR. What you can see here, if you compare it in terms of the interaction design, there's no more paper now. It's markerless, so you can place it wherever. I still placed it on the tabletop in my example. But then we had to think about how do we actually transition between the laws. You can't transition between paper anymore, so we actually brought up this tabbed interface. And Shweta and I regret a little bit that vertical design of that tabbed interface. But retrospectively, we feel like we should have maybe designed this a little bit differently, because we felt like it's not so easy to keep everything in view. But then when I demo it, like the way I demo it here, doesn't it look cool? I think it's pretty cool. So we're actually going to learn in this lecture about the differences in AR experiences, not just in this lecture, actually in this whole week focused on AR. So we're going to spend time on marker-based AR, where the user actually uses a fiducial, like often a physically printed out marker on paper, and that marker is then the portal into the AR world. We're going to learn about marker-less AR, so using the device as a lens into the AR world. And the device then does the hard work of actually doing environmental understanding and figuring out where it is, establishing the 3D coordinate space, so the system and the frame, to really understand how it moves through 3D space. And we're also going to learn about, well, the first two, at least in our case studies, are focused on mobile AR, and I think those are the ones that are very accessible to you if you have a smartphone that is AR capable, supports ARKit and ARCore. or just markers using the webcam or the rear camera on the smartphone. And we're also going to learn about head-worn AR. So I'm going to show you some examples of the HoloLens 2. I realize that you may not have access to that device, but I still think it's very interesting because in the next few years, we can hope at least that the cost will drop and you will be able to use head-worn AR, so seeing the AR world directly and always, and that is interesting. So think about all the evil episodes in Black Mirror if you watch that show. Yes, anyway. So here's a quick overview of how marker-based augmented reality actually works. So you're putting up a marker like this hero marker here. This is based on AR Toolkit. And so it is a default fiducial. You can train your own custom markers. You can customize, you can even randomize in some of the toolkits out there. So Vuforia, for example, which we're going to spend some time with, you can actually generate markers. You always have this kind of trade-off between blending with the environment and optimizing for tracking. So these markers, for example, have to be designed in a specific way. The black borders are important, and we're going to learn about all this. And then what happens is, as the user brings in their smartphone, here like I'm showing this in a second, as the user brings in, holds the phone above the marker or brings the marker into the view of the phone, we actually then see a few interactions going on. We have when the marker is found, we can visualize, we can track it, and we can visualize any content that was designed for that marker. So we show the marker content when it was found, when the marker was found, when the marker was lost. Then normally we would hide the marker-based content. Otherwise, it'll look weird if you just leave it floating, unless you have a transition to markerless AR, which is called extended tracking. So switch from marker-based to markerless. And that's an option that you have if the user has a smartphone that supports, for example, ARCore and ARKit. So in Vuforia, extended tracking is relatively easy to implement. So here's an example of me just doing just that. So I'm actually using this slide. And this is something that if you go to some of our examples, which I'm going to share with you, then you can also just do that and try that out. We also have content where I'm going a little bit more into how to implement these kinds of things as part of the honors track. So if you're really interested in doing this, I have some follow-along lectures there. As part of the main track, I'm going to keep it relatively straightforward, just focused on an overview. So we're also going to learn about markerless augmented reality. So markerless augmented reality works a little bit differently. What you see here is actually visualized planes. These were detected, and we're going to learn about this in detail, how surface or plane detection works. It's a very primitive form of environmental understanding. We'll learn about more advanced forms of environmental understanding as well. So environmental understanding is required to detect physical objects in place than virtual objects in the environment. We're going to learn about plane detection. We're going to learn about spatial mapping. So spatial mapping usually uses some form of depth sensing. So you may have additional cameras for that. It can to some extent be done with just software, so software-based augmented reality. So ARCore and ARKit are actually getting really good at doing spatial mapping, as opposed to HoloLens, which actually has real depth cameras. So we're going to learn a little bit about this. And then the use of obviously understanding the 3D geometry is that we can, for example, render occlusions. So then we can make virtual content disappear if it shouldn't be visible. So if there's a physical object in the way. But here's a very simple example of using environmental understanding. And then there are some more advanced aspects, like, as I said, occlusion or light estimation. Like if you wanted that content to really fit in, blend in nicely, and not stand out like the way it does. Obviously, it's an abstract shape, but it could be some kind of trophy, or I don't know, if somebody ever gives me a medal, it could be an AR medal. Then that would blend in there if we actually adapt for the lighting conditions in this specific area. So we need light estimation, and that's something we're going to not touch on too much. It's just something I want you to be aware of. And there are actually two things in, for example, an AR Foundation that you can control for, is actually on the specific platforms, and ARCore and ARKit, so on smartphone-based platforms, are actually quite advanced there, so they can control for ambient intensity, so apply average lighting to an object, and also color temperature. So actually use white balance to color correct the object. And I'm not really showing this in the screenshot, so what is actually happening here, I'm going to show you quickly the demo. So I'm just going to go here again to my desk. place the object. This is one of the AR Foundation samples that I was just running here. Well, I was proudly deploying it to my phone. Quite an intense process to do this in Unity. And then run it, and then you have basic interactions. This is part of the XR Interactions Toolkit. This is also now native integration in Unity. And then you can like move things around, scale, rotate, and you have support for all that. And the planes that are being detected by constantly scanning the environment in the background, that is the environmental understanding. It's limited to horizontal and vertical surfaces at this stage. Allow you to place these objects in the world. So we're going to learn about marker-based and marker-less. We're going to compare it. Really what changes is in terms of the environment, content, and the interactions really change. So we're going to learn about this, but at the highest level, obviously environment is limited when it comes to marker-based experiences. You actually don't have an understanding of the environment. You're designing around that marker, and the user can play that marker wherever they want to. Markerless is obviously you're trying to get a read on the environment, and that is interesting. And that allows you're more mobile. You don't always have to keep a marker in view, so it enables larger scale in terms of environment. Then content, I mean, something to think about is like how big should the content be appearing when it is relative to a marker, and then when it's like in the world rather than tabletop. If you can also do markerless tabletop experience, but it's more common to do markerless and then room scale experiences. And so that actually has an impact on the layout of the content release and the scale and actually the amount of content you can show. Because for marker-based AR, at any time the marker needs to stay in view unless you have external tracking, and that's when you start blurring these things. And interactions, you can obviously have more implicit interactions with the marker. So I mean, maybe the explicit part is the user has to place it somewhere, but then the app just runs. Or you could have more explicit marker-based interactions, really asking the user to bring things into view to show specific parts of the interface. So in our Kepler's law example, we learn about switching between the laws actually by bringing in a different sheet of paper. And then for markerless AR, we're also going to learn about differences in interactions. Obviously, it could be touch-based. It could also be if it's head-worn AR. It could be gesture and speech, and so we're going to learn about these considerations as well. So think about this example. I'm going to show you throughout examples of marker-based AR. So that's the tabletop experience that I was talking about, and then this is like the room scale AR Foundations example. So this is ARJS, WebXR based, and we're going to learn about this. And I'm going to show you examples here as well. So we have specific lectures focused on marker-based and markerless AR. We're also going to learn about the difference between handheld AR and head-worn AR. So I'm going to bring out my HoloLens 2. I'm going to show you a really cool, well, relatively abstract, but cube example. I built this relatively last minute. I thought I had this idea of how to continue this thread of interactions throughout the lectures. I hope you like it. It was not too difficult to implement. Using the Mixed Reality Toolkit, thanks to Microsoft, was relatively easy to implement on the HoloLens 2. And here's my example. So we're going to move some cubes here. And the cool thing now is, because we have advanced environmental understanding, these cubes, and they have physics, so I gave them physics. They're rigid body objects, and they use gravity. And so then they actually can land on the world. You also just saw occlusion, right? This table here is actually occluding the virtual content. And I'm visualizing the spatial mesh all the time. The blue stuff here is the read of the device on the environment. And then we're going to learn about these interactions. We're going to learn about near and far manipulation, both for VR and for AR. Here, this is AR. I was just doing a far manipulation using that cube. And we're going to learn about all these things. So it's going to be very cool and very interesting. I'm looking forward to teaching you about AR. We're also going to think about design issues. So this is really the red thread throughout the XR MOOC, very important to me. When it comes to AR, really, we need to think about the social and the ethical concerns. There are significant ones because these applications really depend on camera access. Kind of like 24/7 camera access. Need to see anything and everything in order to make sense of the environment. You know where I'm going with this? You get it? Yes, so there are significant concerns. If you don't care, that's fine, but you are going to capture other people, and they may actually care. We have to think about, at least, since we cannot do too much about accessibility at the moment, and equity is an issue. Smartphone-based AR is available to a lot of people in the Western world. But if I did this whole lecture just based on HoloLens, I was like, how many people would actually, I mean, you would probably enjoy it, but you would be disappointed because you couldn't do it for yourself unless you have access to such a device. So equity, and these devices are very expensive, so equity is really an issue. And we're going to talk about that a little bit throughout the course. I really need to make sure that I mention these design issues, because in the next few lectures, we're going to go deep on the technical and the development side. And that's always when we forget to talk about these important higher level issues, including privacy and security. And this is something that I'll come back in week 4, so in the last parts of this MOOC, but really in the first course as part of the XR MOOC, the one that is supposed to lay the foundation. These are really, really important issues. And so I just wanted to make sure again that I'll bring them up. I know as a little bit of a weakness, because we are so focused on the technology in this course, we don't have enough time to talk about these issues. But please, in your design and development activities, we always consider these issues. They should just they shouldn't be an afterthought. They should be built into any and every decision you make as part of the development process. You get it? All right. So I'm looking forward to teaching you more about AR, marker-based, markerless, head-worn. Welcome to this video on our AR design case study. So this is about Kepler's laws of planetary motion. It is both a marker-based and marker-less AR experience designed for smartphones, so handheld AR. It was actually done in an independent study together with my student Shweta Rajaram. We're going to talk to her later as well. So this one is just me showing a little bit the interactions and how things work, both versions. And then we're going to talk to her, and it's going to be a really cool case study. It's also interesting to compare the VR one on the zoo and then this AR one. Obviously, we changed topics a little bit. I'll show you later how you, or at some stage, depends when you see it, how we can take elements of the zoo and also bring elements of the zoo into AR. And obviously, planetary motion could also be done in VR. But I thought, I was doing the solar system for like the entire course too as part of this XR MOOC. If you haven't seen it, maybe take a look. Yeah, I think it's probably too much solar system for you otherwise. Anyway, so this is very interesting. So Kepler's laws are interesting, and we thought actually a great learning experience for students. So we designed this. It was a little bit of engineering work together with Shweta. We haven't actually really implemented it in a classroom. I do think that would be very interesting. We have received feedback from some of our learning experience designers, actually some of the leads there who provided feedback from the Center of Academic Innovation. So that was really interesting at the end of Shweta's project. So this the independent study was longer. So this is really just 5 weeks of work, and I think it's very impressive. So I'm going to show you some of the key interactions here. All right, so this is what it looks like. I'm going to go into the first law here. So basically, this is the marker-based AR version. So we have for every law, we have a separate sheet of papers. You can already see how the planets are moving, and printed on the paper, you can also see some values, and I think that's pretty cool. And now I can start interacting with this and actually changing some of the parameters of the law. Pretty easy drag and drop here on the smartphone. This is done using Lean Touch. So the whole thing is a Unity project, and as you can see, it is a Vuforia marker-based AR experience. I'm going to show you the second law here. So the second law is on a separate sheet of paper. This one is the law of equal areas, and so what we can do is actually we can pause it. So that's interesting. So I tap here, And then we can explore this a little bit more and understand really what this law is about. I focus more on the interactions here than trying to convey the topic. Not too much else going on in the second law in terms of interactions, but the third law is really quite cool. Here we can actually see multiple planets as the law of harmonies, multiple planets rotating, and we can see the values of each of the planets printed down there on paper. I'm going to actually drag that out a little bit here to can manipulate multiple at once or individual ones. So we developed this little flag system here, which I thought was pretty cool. And then I really like it when we have some of these planets really like going outside the paper. I think it's very interesting. We'll get the blue one back, and you can see on the paper down there how the values are there. I'm going to show you quickly, like I would like to show you how we can transition between some of the laws just by looking at different elements of the paper. So here we just have the sheets next to each other, and then zooming in so that it actually, before it sees the marker, and then we can actually trigger it. And it's pretty fun. I think this is a really cool implementation. And this is just the first version, okay? So this is just the marker base. It's actually, in some sense, it's the second version. We did this after the one that I'm going to show you next. I'm going to show you the marker-less AR version now. So this was marker-based just before, and I think it was really interesting. Hope you observed it, how we made use of paper. I'm going to say this a few times. I'm still excited about it. I think this was really cool. Like obviously, you usually have marker-based AR, so you have the marker printed on paper. But often we just cut it to that portion. We don't actually really use the paper for anything else, and that's what we did in this project. We actually did use it for showing the formulas, providing a little bit of the intuition of how the laws work, and I think that's why it's pretty exciting. And here is the marker-less experience. Initially, we have to place the experience. So you saw how I was moving the device a little bit to support tracking, and then I can place it. And now we have more of a vertical design, and we have tabs. So for each of the laws, we have a tab, and I can just like go through these tabs, and it launches a different simulation. You can see how it changes the content down there. And I just like how everything is always running and interactive. And so let's play with this a little bit. So we can use touch here, just like before. And then I can move the flag around and then actually adjust the parameters. And we do print the values now in the tab at the back. So in the graph, in the illustration, you can see how it changes there as I drag. And obviously it also changes the rotation, so the orbit. But I really like how the values update in this illustration up there as well. Let's go to the second law. So the second law is kind of like similar to the marker-based version. So it's just playing that thing, and then I can actually pause it to observe how this area can be estimated. So a line segment connecting a planet and the sun sweeps out equal areas over equal time intervals. So that's what the law is about, and it's illustrated here. Let's continue. So now we're going to the third law. And I always say this in a funny way. It is the law of harmonies. And so, trying to make fun of myself here. Anyway, so we can drag things around, and you can see we don't have any kind of placement issues. Obviously, we can update the values nicely in the tab. I'll show you one more time as I drag things around. It's just like fun to observe these planets. And you can go closer. You don't have to pay attention to anything markers. So you can zoom in. You can follow individual planets. You can drag this out and drag it back in. Now this one is floating a little bit out there. So that's cool. And then we drag it back in. Bring this planet back onto the sheet. So let's do a little bit more fun here. And you can see how the values update up there in the sheet. I was about to say it's not a sheet of paper anymore. Anyway, this is cool. I enjoy watching this. And I think it's great. Thanks again, Shweta, for contributing this AR design case study. So both marker-less and marker-based. Again, this one was actually the first version we created, and then in the last week we did the marker-based adaptation. When you think about it, it's actually pretty impressive. Such a short amount of time. So obviously she did one of my courses, and she was already well versed in Unity. And but she wanted to go deeper in AR, and that was what the independent study was about. And I thought it was a great case study here for our XR MOOC. And so we're going to talk to her next, and let's see what she has to say. I have a few questions for her, and I hope you find this interesting and useful. I really enjoyed the project and working with her, so it's great that we have it here in the XR MOOC. In this video, we're going to talk to Shweta Rajaram, who actually contributed to the MOOC, her AR project. So it's an exciting project that was done in an independent study with me. Well, that's not why it's so exciting. It is exciting because it involves both marker-based and marker-less AR. So it's actually a really good learning opportunity for us. And I've actually invited Shweta to talk to us about her project. So Shweta, hey, how's it going?
It's going pretty well. Thanks for inviting me.
Sure. Yeah. So, the project is really quite complex. I feel like the main key milestones were like finding a topic, like selecting a topic, implementing things first with marker-less AR because you already knew about AR and you wanted to do an AR project, and marker-less AR technology seemed like very interesting to us. And then in the last stage of the project, we actually played around with marker-based AR, so which to many people from a technology perspective seems inferior to markerless. So why use markers if you can do markerless? Is that also how you remember the project?
Yeah, I think that's a good description of the key challenges that we faced, or like key decisions that we made at the beginning.
So yeah, that's great. So we're going to talk about this project, and we're going to tackle this issue of picking a good topic for AR. And to help us and support our discussion a little bit, I actually brought back the presentation that you prepared about the project that we used to discuss it and present it to various stakeholders here across Michigan working in the XR initiative. Let's talk about topic. So you chose Kepler's laws of planetary motion. Why were you excited to actually do this as an AR project?
I guess the overall motivation for this project was to get a sense of if we were instructors trying to create an AR experience for our class, what kind of challenges would we run into? And I felt like Kepler's laws was a pretty complex topic that involves some like mathematical simulation. It would have interesting interactions, and it just felt like a sufficiently complex topic. So a good learning point to see where instructors would actually struggle in trying to create something like this themselves.
Right. Cool. So, and yes, so we started out. Let's talk a little bit about process then, which I think was very interesting. So I think this was an independent study, so it was semester long, but we did some other things in the first half. So what we're talking about now is about 6 weeks of work, maybe. Is that about right? Just okay, get a sense for that. Cool. All right. So yeah, topic. So let's start with our process. Sketches. I remember, well, you have a very creative background. So in arts, I remember you sketching a lot. So I'm going to bring up some of your sketches. And I was thinking maybe you could use these sketches and, walk us a little bit through some of the ideas you had initially.
Sure. So I guess I am a person who really does need to sketch things out for media and the idea of what I actually want to develop. So here are a few of the ideas that I had. The left two pictures they were my initial ideas. So for marker-based AR on the left, I had some ideas around attaching a planet to a marker, and then the users can kind of move the markers around in the physical space, and that would affect the simulation parameter. So maybe if you move the planets closer together to the sun, the orbit is going to decrease in radius. Yeah, so that was one of the ideas that we didn't actually end up implementing it that way.
But it seemed like a cool idea at the time, and it allowed you to brainstorm through some of the interactions and thinking about marker-based AR. Okay, and then markerless AR, what were you thinking there?
So I was also thinking about a tabletop experience for markerless AR, which is kind of an odd decision in hindsight. But the idea was to have three base visualizations, or sorry, one base visualizations with three different changes that we would make for each of the three Kepler's laws. So we were thinking about mobile AR, so using my iPhone, and there would be a few on-screen interactions to move the planets around or stop a visualization and pause it and kind of learn how changing the parameters would affect other things in the simulation.
Yeah, so mobile AR, so students and instructors would have a smartphone or a tablet. And you said tabletop. Why was that not a good idea? You said something like in hindsight it wasn't the best idea. Why did you say that?
Yeah, I think if you think about markerless AR, you need to scan the area quite a lot to get stable tracking. Um, so that's pretty easy to do with marker-based AR. I think, in hindsight, maybe that would have been a good starting point if I wanted to do a tabletop experience. But I say it's a little strange because you don't really intend on scanning the whole area for a tabletop experience. You just intend on looking at something when it's right in front of you. But I think markerless was really cool to explore with scaling. Also, we tried that I think a little bit, scaling it up so the planets are like flying around you and could make something a little bit more immersive that way.
That's right. And had we had more time, we would have even taken it further and maybe tried it out on HoloLens as well, which in some of the other projects you have implemented HoloLens experiences. So mobile AR. Well, I think it was a good technology choice for the classroom. I think marker based, markerless. Ultimately, we supported both in the project, which I think is cool. The interactions changed quite a bit, so I want to talk to you about how we thought about that and how we thought that through. So obviously you have all three laws kind of like implemented, and we can run simulations of these motion laws in both markerless and marker-based AR. So then this project was about marker-based and markerless AR, and the interactions changed quite a bit. But so it's during the implementation and development phase. But in your earlier sketches, can you walk us through some of the interaction ideas you had?
Sure. So I guess one of them is the moving the planets was kind of like a constant idea, but we had different ideas on how you'd actually achieve that. In earlier implementation, it just kind of had you clicking on a planet and dragging along the axis, like the semi-major axis of the ellipse. But then later we kind of figured out that we also wanted to show how calculations of within the simulation might change, like if you extend the length of the radius, how fast would the planet move? Would it slow down? Would it speed up? And actually show mathematical values to support that. And we kind of found that it was hard to know what parameters you were changing just by dragging the planet, because it really depends on the geometry of the ellipse. So kind of in the top of that right hand sketch, we changed the design a bit so that you're dragging this little flag that extends from the center of orbit to the planet itself. And on that flag, it prints a value of how long that axis is.
Well, that's cool. So now we have a first overview of the interactions you had planned at the sketching phase and storyboarding phase, which is very important. And then soon, I mean, because you were already experienced with these technologies, we really went very quickly into development and prototyping. So we started with markerless AR, basically a phone that supports ARKit or ARCore, smartphone is the device of choice, and then we would experience your laws. So can you walk us a little bit through how you developed that AR experience, the markerless experience? Were there any particular design choices you made and design rationale for those? Or you can also talk about any implementation challenges, because this is really the course where we want to learn more about developing AR experiences.
I guess one of the decisions that we made is that we wanted to try out this same experience for like a desktop version, a marker-based version, and a markerless version. So knowing that at the beginning, I kind of structured my Unity project that way, structured my development workflow that way. So for every new feature I added, I would start out with this desktop version and just get it working within the Unity editor. And then I would try to adapt it for Markerless AR since I decided to do that one first. I kind of worked on the marker-based version more near the end, but that was the basic workflow: get it working in the Unity editor, and then test out on my phone and try to see if there are any other issues that came up. I guess implementation challenges, there are definitely quite a lot, I think, even from transitioning from desktop to AR. Coordinate systems was something that I had a little bit of issue with. Once you're transitioning to AR, the scale definitely changes once you put it in the world. And with all the animations that were happening, kind of a lot of my calculations were based on world position, when sometimes it really should have been based on local positioning between the elements. So that was one thing that I definitely struggled with. I'd say also creating the second law visualization was pretty difficult because it involved a lot of real-time calculations about how fast the planet was moving, and then trying to calculate the area that it was sweeping out at that point, which is effectively an integration problem, which is, you know, pretty hard to implement in Unity. So I think I experimented with doing an estimation instead, but it just wasn't really working out. So I think that was one kind of compromise that I had to make. For the sake of just creating this proof of concept, I thought, okay, it's okay if I just hard code one set of area values to show what I intended this interaction to look like.
Those are good insights, actually. And obviously, yeah, I can really hear the experience of going through that project and learning about some of the implementation choices. So, technology-wise, it's a Unity project, you said. We used AR Foundation that allowed us to compile to both ARKit, and you were using an iPhone, or maybe you were also using Android in this project. But I know that I was able to also try it out here and show it to the learners. So, technology choice, do you feel like that was a good choice, using Unity AR Foundation, going that route?
I think for me, I think it was the right choice, I guess, because I am more familiar with Unity. I think if I had to implement this in A-Frame or some other technology, I probably wouldn't have been so confident and probably wouldn't have been able to do it within that 6-week timeline. If you think about actually deploying this, I think, you know, in a classroom or for instructors and students to use, it would be pretty difficult to have everybody install it on their own device if you don't have access to just devices that you can hand out to them. So yeah, I think definitely some drawbacks.
Yeah, so deployment is well, but I think you have a good reach with the technology choices that you made. Yeah, Unity versus A-Frame. I mean, that's an ongoing debate in the lab. WebXR versus Unity, and now also we're doing more and more stuff in Unreal. But I think ultimately it's a really good, like what you're saying is really, it's really true. Like, it's a reflecting on your own skills, maybe what do you want to learn. I remember always asking you, what do you want to learn in this independent study? Where do you want to grow? And I think ultimately I'm actually really happy with the technology choices you made. So I want to look a little bit more at the actual markerless version of the project. So the way it is designed, so implemented in layman terms, is a tabbed interface appears above a table. We see 3 tabs. Each of these tabs is dedicated to each of these laws. And then you're running a simulation with planets rotating around the sun, and I can actually impact their rotation by drawing flags. I think you talk about these flags, and I can nicely switch between these different laws just by switching to the tabs. And what I really like about the project is that I actually see the formula, so behind all this, the calculations, that you actually fill in the values. So it's interactive and allows me to explore how these values change when I drag around the planet. So, okay, so that describes roughly the interactions you can do in the markerless AR version. And so which of these design choices are you happy with, and maybe where would you have liked to make other decisions now thinking about the project?
Yeah, so I like that we tried to integrate a lot of different learning components. So there's a visual simulation that you can watch, you can play with, and see what happens kind of at a high level when you change the parameter. So you drag a planet out, the orbit's going to get bigger, and then the speed should also slow down a bit when it's further away from the sun. So I think that's like a pretty simple connection that you can make for maybe more advanced students, or once you kind of get the base idea, you could probably start reading some of the stuff on that card that we had there. So you can look at the formulas and see how the calculation is actually done. So I think it was pretty challenging to figure out how to integrate all of these components together, because you have some 2D elements like the panels, and then some 3D elements, the visualization. I think definitely there could be some more experimentation with how to actually organize that content within this theme. Because if you actually try out the experience, you watch the video of Michael trying it out, there is a little bit of context switching that's going on that wasn't the easiest to do on a small phone. You have to look down, like a bird's eye view of the visualization, and then keep switching up if you want to see the values changing. So I think definitely there could be some improvements there.
Well, so in the marker-based AR version, you then have changed quite a bit of that layout and design. So when I try it out, the way I look at it, I place a marker on a table. That marker is actually embedded nicely in a handout. That handout actually then tells me more about the experience, about the laws, and it's actually a really cool experience to have it like flat on the table. And then you run the visualization like it's embedded in the paper. I think that's really exciting. So I feel like you have changed the layout quite a bit. Was that because it was in some sense a second iteration of this project, because it's like the marker-based version you did last, or was that a specific design choice you made for marker-based AR?
I guess kind of both. From testing the markerless version, I think we both realized it was a little bit hard to do that context switching, but also I think just having a piece of paper there affords putting more information on the paper instead of just all within the virtual environment. So that was a design choice I made because I wanted to explore that side of it also, like if more of the content was physical.
Yeah, I like that, especially about the project. In many ways, the marker-based version is actually my favorite in the end because of the really nice way of how you integrate it with paper, and it also inspired some of our ongoing research at the moment. So I think maybe we're taking some of these ideas further. I think it's a nice blending, the physical and the digital, and I feel that is what AR is really about. Like in this project, I feel like we talked many times about scale and accuracy of the simulation, and is it even like, is the distance between planets even like accurate and all these kinds of things, so which doesn't seem to be the case. So there is no spatially consistent relationship. So the primary use of AR is not necessarily of bringing it into the physical space. So then that's why I really liked how you made use of the paper. Like basically it enriches paper, and now it becomes an interesting learning experience. Well, that's my view, but how do you think about it?
I agree. I think I definitely liked the marker-based version a bit more. I think the reason that I had started with markerless is because I really thought it would be an issue to keep the entire visualization in view while also looking at the marker. But it turned out to not be so bad. I also really liked the navigation method with paper. I mean, you could just scan a different marker, like move on to a different sheet of paper. And I think that format it feels a lot more flexible in terms of like what activities that you could do. Like you could make it into a workbook, or they have these kind of like poster walk activities where teachers put little like demos or activities at different corners of the room, and students can kind of rotate from one to one and explore on their own. I think the tab setup was also okay, but with the paper, you could more easily compare what's happening between the laws if that was useful to you.
Yeah, and I think you had a version where multi-marker tracking actually worked, so I could actually put all three sheets of paper next to each other and see the three laws next to each other. Is this correct?
Sort of. In theory, if I had gotten the coordinate system right at the end, I think you would have been able to do multi-marker tracking. But I did kind of like a hacky fix at the end because the way that the Vuforia coordinate system works is that it can be where the device is, I think, if you're doing extended tracking, or it can be attached to a specific marker. So like 000 is attached to a specific marker. So In that case, which is what I ended up doing, attaching it to a specific marker, you can't really scan multiple markers because then all of the planets would try to rotate, I think, around the first marker that's scanned. So instead, whenever a marker is found or lost, I kind of change the coordinate system based on that. So if a new marker is found, that's going to be our new 000.
All right, yeah. So, and now you're getting quite technical already. So it's like, okay, that's cool. Yeah, and so our learners will learn more about this. So they learn more about marker based. We actually start with marker based. I still think maybe this is a good way to teach it. Hope you agree. And then we're doing marker. Yeah, you think so? And then we're doing markerless AR. And so to me, it's just interesting and unique to this project that we explored all of these, including desktop, markerless, marker-based, and then the order in which we did things, which I think is pretty cool. So I want to bring up the project timeline quickly, so that we can share that a little bit. So I'll put it up here on my screen, and it looks like it's a 5-week project. So to me, it's still impressive when I look at this because it's really a lot of things you can do, and then you change the interactions between marker-based and markerless AR. But okay, so here's the timeline that you put together. Can you walk us a little bit through this timeline?
Sure. So first, like you saw, we sketched a little bit before getting into development. And then I started prototyping the first law. So again, starting with the desktop version and then the markerless AR version. I guess what's a little strange is that I moved on to the third law before the first law. So I kind of chose that in order of difficulty. I thought I would really struggle with the second law. So I figured, let me try to get the easier stuff out of the way to make sure that I do have some kind of an end project. And then in the middle, we did kind of redesign the user interactions after trying out the first law and third law and realizing that we wanted more of a connection between the mathematical calculations and the user interactions. And after getting a pretty solid version, so kind of week 4 is when I started adapting for the marker-based experience. And it was actually a pretty straightforward transition, I think, more straightforward than I thought. And probably because of the way that we had structured the project at the beginning, we're trying to just keep a desktop version that's always working and adapt it specifically for other kinds of AR and potentially VR as well.
That's cool. And then also project management wise, I know that you followed a few strategies because you've taken other like game design and development courses as well. So what was your usual workflow? Like when does a feature make it into the project and how did you go about some of the project management more?
Yeah, so like Michael said, I did take a game design course, and that's where I first learned Unity. And our instructor there really stressed creating these lab scenes, like a laboratory, like a little where you can run like a little experiment on a small feature before trying to integrate it into the rest of the code to make sure that it works on its own before you add all of this other complexity to it. So I did follow that. I prototyped each law in its own lab scene, and then when I was satisfied with it, I would move it into the main scene and then connect it to the theory visualization and to all of the other parts of the scene. I guess also just to keep organized between everything, I am a big note taker, huge fan of that. Maybe too much sometimes, but I think it's really helpful to maintain a document or something where you can note issues that you've been having. Sometimes I even put down tasks that I've worked on for a specific day and how much time I spent on it, just so I make sure that I'm using my time well. And then definitely links to like Stack Overflow posts or just anything that you found helpful. Sometimes even in future projects, I'll run into issues and then think back to where I've found that issue before and look at my Kepler's Law research notes to figure out exactly what steps I took to solve that problem.
It's funny how you made the comment about note taking. I think that's really important because and also how you spend your time, because sometimes it feels like an endless loop. Something that seems to be relatively easy turns out to be very difficult to implement, or you just don't know how a feature works because it's not really well documented. So you really being smart about your time and then taking notes so that in the future you can revisit some of the lessons you've learned in the past. I think that is actually a really, really important thing to do. And I would encourage our learners to do that as well. So I really actually like that. So no need to apologize. I think the notes were really helpful. Also, like when we revisited this project now, to present it in this MOOC. I think it was really easy for me to set it up again and get it to work and do the demo and then prepare for our discussion here. So we've learned quite a bit. Markerless first, marker-based last is kind of like what we did. So I find that still fascinating, and so I have two questions for you. First of all, do you think in your next project or in general it makes sense when you do AR to explore both marker-based and markerless, or and do you have any kind of like, would you do marker-based first and then markerless, or how do you think about, like, are they both necessary, or can you eliminate one of these even earlier? I don't know. So it's an interesting decision to make when it comes to AR.
Sure. So I'd say I think it really depends on what you're designing for. The reason why we did it is because our intent was really to learn about the challenges with marker-based versus markerless and what an instructor might go through when making this decision for their own classroom. I'd say, in my case, since I was doing a tabletop experience, it could have been smarter to just start with the marker-based version. Although I think maybe the result might have been a bit different. Maybe we'd have had two completely different simulations, one where you're actually using the physical space a bit more to move the markers and move the planets, and then maybe something for markerless more similar to what we ended up with in the end. I wouldn't necessarily say that you have to implement both of these versions. I would recommend always starting out with the desktop version, because then as you saw, it wasn't too difficult to actually adapt it. So I would say start with desktop and then move to AR or VR.
Yeah, VR could be another channel. Even I think in this project could have been interesting as well to then also bring in VR and see which of these modalities is ultimately the best for this kind of learning experience. So I think this is a really cool project. So our MOOC learners can learn about the technologies. We will go deeper into marker-based AR first, learn how to do this with A-Frame, and then also learn how to do this with Unity, and what kinds of technological choices we have there, how to reach smartphones, how to design for headsets, which are not very widespread at this stage. So the choices we made around smartphones and markerless and marker-based, I think, are really cool. And what I really liked is ultimately what you're doing in this project is, because you can support these different kinds of configurations, the choice is ultimately with the user, which in your case it might be the instructor or the students even using it in a course. So if you're telling me that because of how you structured the project and how you have implemented it, that overall it wasn't actually so time consuming to support these different uses of AR, and that might not be true for every project, but then I would just say this really goes well with the idea of empowering users, and whenever you feel like you can't make that ultimate decision as a designer, why not implement a way so that users can make that decision? So now that raises maybe some deployment questions. How would you get these different versions? Is it easy to switch? Can you package them into like one Unity app? We haven't actually deployed it yet in a course. That's something that we'll talk about as part of the XR initiative. I think we foresee some challenges there, actually getting it into the classroom. But I really like that project because we can learn from it.
Yeah, it was a really fun project for me as well. I liked that we could focus on development, but then also be kind of critical about some of the design aspects, and then brainstorm around how this could actually be used. I think neither of us really think that it's a perfect experience, definitely a lot of improvements, but I think it's been really useful as a point for learning, and now we can build off of this for future projects.
Yeah, and that's fine. I mean, everything is a prototype, and I think we learned a lot from that project. And yeah, I'm not sure which design decisions, like if we had to do it again, not going back in time, but just like doing another iteration. It's interesting to me. Do you have some ideas of how you might take it further? Are there some features that you feel like you haven't implemented, or would you change the design completely? Or how do you think about any kind of extensions to the project?
I guess I'm thinking back to at the end of the independent study, we had a conversation with a few people, and one of them was a learning experience um, expert, I guess you could call her. And that was really helpful to hear her insights about what learning goals the instructor and students would actually have from using this experience, and whether the AR simulation would actually fulfill those learning goals. So I think it would be interesting to think of a redesign, and to look more, I guess, into the learning experience aspects of it.
Yeah, I don't know. I mean, obviously, getting the input from the learning experience designer was very good, and it's just something that is difficult to integrate in an independent study, right? Bring in all these stakeholders. Whether a complete redesign is necessary, I don't know. I don't know whether we would have ended up with a different design, but it's like in the nature of the project. We wanted to explore which of these technologies are actually better suited. Wanted to learn more about these technologies. And so I think even in that sense, that project is very relevant because a lot of people out there are actually experimenting with these technologies. We don't have a lot of guidelines. So I feel like we just have to do it. So learning by doing. And yeah, when we reflect on this project together, you're not saying, and this is in your nature, I know, but you're not saying this is the best thing that, this is the ultimate design and every app should be designed this way. No, obviously you're not saying this, but I mean, maybe we would have more confidence in some of our design choices if there were more established guidelines. And right now, I think you're filling a really cool gap with this project. Well, first of all, our learners can learn about marker-based and marker-less AR. So we're actually going to really inspect that project. So don't be scared. But we're gonna learn about this, and I'll mix in some other things. So that's really part of the idea, to learn about these technologies, but based on one example. And I think this will be actually really exciting for our learners. And supporting the learning experience with AR technologies, I still think as a topic, that is actually pretty cool. Even we're doing more research in that space now. So I think there is even a lot of future value. And even going through the exercise of actually deploying it in a classroom and learning that way, that is ultimately would be so fascinating. Maybe you wouldn't want to take Kepler's law. Maybe you would do something else. But I think I really like the project. So thanks again for sharing your insights with us. And I'll let you know what our learners think and where they struggled. And maybe we'll bring you back if there are some questions. So thanks again, Shweta.
Thanks.
In this lecture, we're going to talk about marker-based augmented reality. So now we're going to really focus on markers, marker-based design, what are the interactions, what does this mean for the content. And we're going to do this again based on our case study, Kepler's law of planetary motion. So while we actually designed the marker-less version first, as I was discussing with Shweta, we explained why we wanted to do that first. We then, in the last parts of that independent study, actually then implemented the marker-based AR version. And we realized how cool it is, really designing around paper, doing these marker-based augmentations around paper. And actually, it is a current theme in our latest research. One of Shweta's first projects is part of a PhD thesis, so it's going to be exciting. I'm going to show you what we have created at the time. It is the marker-based AR version. It's a longer video of what you've seen before. So I'm going to zoom in a little bit. First law, you can really go in there. You can lean in, and there you see it. It's pretty cool. And you can see how the values are actually projected on paper, and also how some of the values change. As I start interacting with these flags, they determine the orbit, and that changes the values for the law. And so that's pretty cool. You can see how I'm touching. I'm switching between what I see directly through the camera, and then you sometimes see a little bit more in context as I'm wearing the GoPro to show you this stuff. So the second law, did you notice how I just switched between the laws? I was just bringing a different sheet of paper. And so that means we can actually we can deploy an application like this and actually make it very easy for example, students to operate it, because like we don't actually have to learn too much about the interface. Okay, maybe that you can click this to stop wasn't exactly clear, but that's something I could show as an instructor as well, as I'm guiding my students through this. And here's a lot of stuff going on. We have a couple of the law of harmonies. Always sounds funny when I say it, but anyway, that's just me. It's pretty cool. These actually then, the way they rotate, the way they orbit around the sun is constant. I didn't actually say this right, but this law is just fascinating to me. So it's cool, and it's actually cool when you drag this out really out of paper. Let's focus on the interactions more than me trying to explain what's really going on. That's not as important. But here I'm showing like how we can transition between these. We could probably also implement a version where we can show all three laws next to each other, doing multi-marker tracking. But this works as well, right? As we switch the focus, actually keep in mind, these actually are relatively complex simulations that Shweta implemented in Unity. So there's actually some math and computation involved. I remember her complaining a little bit about this in our independent study, but she did a really good job. And I think it's cool. Like, it looks really nice. The transition is very smooth. It does remember state. So it's a lot of stuff going on there that we need to learn about. And so let's just do that. Marker-based AR. So we're going to talk about marker-based tracking. This is really clearly the enabling part of this, the enabling technology. We're going to talk a little bit about marker design. And I think in this case study, we can learn quite a bit because of the way we're making use of paper and how we're printing information on paper. Yes, we are printing information on paper, but we're also projecting using AR. So we're visualizing things on paper. And that's what I'm particularly excited about. And we're going to also learn about a few marker-based applications. This is the part where I'll then release a little bit from that case study and look at other examples as well. So let's start with marker-based tracking. So marker-based tracking here as an example with ARJS. What I'm showing here is place the marker on this surface, and I'm showing a virtual copy of that marker. That virtual copy disappears as I occlude the paper. The tracking then stops working. So no extended tracking, but that's just how it is. In this case, when the marker is lost, we hide it. When the marker is found, we show it. And then we constantly track it and adapt the scale and the size. Sorry, the scale and size is the same, but the pose, so the orientation and the rotation, that is also the same. What am I doing? So the position, the orientation, and the scale, that's the transformation matrix. Okay, you see it better in this example. So we're gonna show this virtual cube here that is supposed to fit perfectly onto that marker. It's a red cube sticking out, and I'm showing both the marker, how it's tracked, so a virtual copy of the marker, then the actual virtual object, which is not too interesting, since in this example it's just designed to show you how tracking works. When I pick it up, it's also interesting. You can actually move a marker, especially a marker this size. If it's smaller, it's harder to track. But you can move it, and it actually works. It's very robust, to be honest, even though this is a technology from 1999, AR Toolkit. That's what it's based on. Cool work from University of Washington. And it actually did enable quite a bit. So we're going to learn about AR Toolkit. A lot of people probably now just go ahead and use Vuforia in Unity because it has nice integration with Unity. But ARJS is based on JS AR Toolkit, and JS AR Toolkit is actually a JavaScript port of AR Toolkit. So it makes sense to learn a little bit about this. So how does it actually work? So I'm going to walk you through the steps. So here we see one of the frames from the video just before, where I bring the marker into view, and I already show the virtual object. So we are extracting the original image, and then we're building some kind of, well, not we, but AR Toolkit is building a threshold image. So it's actually, I'm approximating this here. This is not exactly how this looks to the algorithm, but basically you're doing a threshold image. And then you're looking for the connected components. In this case, the label inside there is actually significant. You're building contours, so get a rough shape I illustrated this here using my amazing Paint.net skills, not even Photoshop. This is roughly what it looks to the system. So just getting the contour, the shape, actually the outline. Think of getting the outline of the marker. So getting the rough shape, and then detecting the marker edges. So we have both the connected components, so the hero in there and the edges. And so then we can extract the marker, and then we can fit a square on it. So it's a fitted square. This one is the bottom plane. Okay, if you were like, I had an optical illusion for 1 second as I was looking at the screen, but so this is the bottom plane and this is the top plane. Okay, so it's really sticking on top. And then when I put all the pieces of the algorithm together, this is the result of it. And that was a quick rundown of the algorithm. So here we have the marker that we just saw before. It's called the hero pattern. It is one that is a default pattern as part of AI Toolkit. And so let's talk a little bit about marker-based design. So this one is really significant. The continuous black borders around it are important. They are key. Okay, so don't occlude them. So don't hold it like this or cut things away. Okay, so I've actually built a little latch here at the back so I can just hold it, and so that's how I'm doing it. And I'm going to use that later. I have something funny prepared for you. I mean, funny, relatively funny. The experience I really wanted to show, which is Disney's Toy Story, couldn't do it, but I'm going to show you something else instead. Anyway, so marker-based tracking. So back to the rules here. So you should design these markers, and when you print them out, they should be bigger. The smaller they are, the harder they are to detect. Detection is one thing, but tracking is really hard even. And the size of the marker really determines the object scale. That's something when it comes to implementation. So 1 unit is actually, this is 1. This is 1 unit. So if you put a box on it of scale 1, it actually fits nicely onto that box. Okay, so I'm trying to do this in a way so that it makes sense for you. So I have my marker here, okay? And I was talking about scale. So if I actually bring in a different size marker, it'll be smaller scale, okay? So I now happen to have a different marker here, one that I always carry with me, my favorite marker. You see the difference? Harder to track, smaller in scale. I didn't change the code. It's still a 101010 scale, but you get it? Let's go back. I'm glad I was able to show you this. So I'm going to now go back to my slides here. So that I was just illustrating how the size of the marker determines the object scale. So pay attention to that. And the content inside the marker can be customized. That's really important. So inside the marker, right? It says hero here, but it could say something else in there. I don't mean the virtual content that you place on the marker. That's obviously completely customizable. But I'm talking about the marker design. So we can also do custom markers. So there is a number of patterns. ARJS, for example, has a pattern generator tool. And Vuforia we used to generate markers. Actually here, well, we generated this part of the marker. And we built identity in this marker. And then we printed that marker on the sheet of paper. And then we are aligning some of the augmentations relative to that marker so that it appears on the paper, including filling in some of the formulas here and some of the values down here. Doesn't always work perfectly, but I thought it was a really cool idea. And then here, what we're doing is we have the explanation here and we're running the simulation up there. What we could also have done is actually not occlude this marker, occlude this content, use this marker for tracking, and actually show the content here. But we wanted to be consistent as we were always running the simulation up there, but we could have done more to this lower part of the marker, and that's something that Shweta and I had discussed, but we were just running out of time at the end of the independent study. And it's not necessary because the project is cool enough anyway. So, and then we had Kepler's third law. There was a lot of stuff going on here. You had multiple things you could manipulate. The law of harmonies, I'm going to say it again. And then we filled in the values down here. Again, using that marker to track. In that marker, you can see how they look different. I mean, maybe you cannot see, but the marker engine, the tracking engine can see these are different patterns. And you can see it if you focus on specific aspects of these patterns. Then you can see, like, if you focus on this area, then it looks different here and it looks different here. Do you know this kind of games where you have to look, like, compare two pictures and find all the differences and then highlight them? These detective image games? I don't know. Anyway, so that's what we just did here for a second. And then we are running, I'm showing you a little bit me going towards these markers. Nothing is happening here. I'm just showing you actually the paper that we used with a little GoPro here. And this is how it appears to the student. Let's say I distribute the sheets of paper to the students. This is what it would look like. And you can see the marker pattern printed up there. And then think of that whole paper as the marker, not just the pattern up there. Because we're designing the content relative to that paper. So the whole paper functions as a marker, but we identify it based on that pattern up there that's printed up there. So the sheet of paper is the marker, if you will. So basically, any object can be a marker. Okay? If you're using the right frameworks and tools, you can do all of this. You can use QR codes and barcode scanners, so they can also encode a URL. So you can use it both for tracking, but also for redirecting people to a specific website. Faces can work as markers, images and photos. You can train existing tools like Vuforia on images, photos, and even more. And there is actually face-based marker tracking, so Snapchat's Lens Studio does that significantly. ARKit and ARCore have support now for face tracking, and so you can do all that. You can have 3D models function as markers. So it could be any 3D object, but it could also just be, so maybe you saw this guy from time to time. This is actually a present from my mom when I graduated with a PhD, and I still have it. And so this owl was supposed to be visible from time to time. It's quite cute. And we could use this as a marker. Yeah, we could train some software on an object like this. It's not straightforward because this is a stuffed toy. But it would work. And Vuforia, for example, has some basic support for that. You could use indoor locations, so using environmental recognition and then pre-scan these areas. So it could be based on photos, but you need a series of photos. It needs to build really the 3D geometry, so photogrammetry would be used to really understand and detect these areas from different angles. And then buildings, like usually like a facade, like the front of the building, the principal front could be detected. And that's really cool stuff you can do with that, especially when you combine it with projection-based AR. So you could actually project and augment against that building. There's really cool stuff out there. Disney is a master at this, and so that's how this stuff works, okay? So here's me doing face tracking in Snapchat. I kind of felt like I have to show this. So we're going to do a facial lens. I want to show face tracking. So I'm using a tool called Lens Studio here. And Lens Studio is behind a lot of the Snapchat lenses, if you're familiar with Snapchat. And so there's a lot of examples out there. And maybe as I talk about this, you're imagining all the things you could do to my face. But we're going to do something meaningful in this example. So the scenario is we are going to a conference. And you meet me there, and you get to see some information about me. And so like a badge, okay? And we're going to do an augmented reality, like a virtual badge. So I just downloaded that badge that I prepared. I'm going to add it to my project from this file that I just downloaded. Here we go. That's the example. And what I'm going to do is actually add it to my face. So I'm going to do a face image. And we can think about where we're going to place it. Right now I have it like in my face, and that's exactly where it's going to be. And that's not what I had in mind. So I don't want it like this, and I don't want it like that. That's not meaningful. I'm thinking we're going to put it relative to my face, maybe a little bit closer. And it would be good to anchor it between the eyes. I think this is like kind of like the best example. And so let's say you meet me at the conference, and then you could ask like your augmented reality glasses that you're wearing right now, could do some gesture. or it just like it knows when it looks at people, it should show you this information. And so this is the information that it could show about me. And could also be other information, obviously, but this is an example that is not so far-fetched. What's the main reason Microsoft bought LinkedIn as they are investing into HoloLens is something you could ask yourself, for example. So yeah, that was that example. Cool application. I think this is a better application than some of the other things you could do to my face, but I'll leave that up to you. And so in terms of marker-based interactions, let's come back to our case study. So there's a number of things that are going on there. You can place the sheet of paper. You can point on paper. So I use the hand behind the phone here. You can tap on the screen, and you can drag things on the screen. These are some of the marker-based interactions. And even these are still marker-based because you have to keep the marker in view. Otherwise, you wouldn't even see this content. And so it is an interesting relationship between the device and the marker that we're exploiting here to support these operations. So placing looks like this, right? You're bringing the sheet of paper into the view, or you're placing it somewhere on the table. That's how I had it. Pointing, again, it's pretty cool. Keep in mind that unless you have people segmentation, which is a technique to really segment these hands and fingers out, you will always have the AR content appear on top of the finger. So you pointing into the you're pointing at the paper. Keep in mind that the AR content will appear above your hand, not behind. Your hand will not occlude the content, and that's a limitation at this stage. But maybe when you watch this video, maybe this has been solved already. Anyway, in 2020, when we didn't have anything, like we didn't have occlusion with marker-based AR, Anyway, so then tapping onto the content and dragging. So dragging these sliders around. This is something that we have implemented using Lean Touch. It's one of the libraries you can use in Unity to do touch and multi-touch based interactions. So far in my examples, we've mostly either placed the paper or sometimes put the paper in view. But you can actually design very specific interactions for that. I'm going to show you these differences quickly. So here, I'm bringing the marker, obviously, into the view of the phone. I'm holding the marker, okay? And that's a way to design interactions. But keep in mind that that would mean that the user has only one hand to hold the phone and one hand to hold the marker. So it's not too much they can do. And this is different, right? Placing the marker gives more. I don't have to hold the phone with two devices. If I were using an iPad, I would have to hold it probably with two hands. Did I say two devices? I meant two hands. And so that is a difference. And now what can we actually do with marker tracking? Well, we can do something funny like this. So here I have an example of using markers for puppeteering. So I'm a giraffe. It's nice to meet you. Welcome to my MOOC. And let's go. And we can also have two. So, hey, what's up? Have you heard there's this interesting news? Yeah. Oops. And then yeah, I have. And it's also, by the way, it's good to see you. And I'm going to show you how it's done. So here I have an interface where I can actually change the opacity and show you the magic. Now that takes away from the illusion, but all I'm doing here is puppeteering with markers. And this is for storytelling, but it's just like I wanted to illustrate that marker-based AR can be used for rapid prototyping. These could be interface elements. These could be all kinds of different things that you want to experiment with, different layouts. Obviously, you can align the models differently. It doesn't have to be models. All kinds of flexibility there. And you can use this for prototyping VR interfaces or AR interfaces as well. So, I mean, the actual video stream that you show here doesn't have to be this one. So, lots of flexibility there. And this was just an illustration of what you could do with marker-based AR. And now we're going to go off. I'm a giraffe. Nice to meet you. Okay, yeah, I definitely had fun there. So let's review some of the marker-based AR applications. So Marker-based AR is really a good option if you want to reach low-end devices. If you're not just assuming that everybody has the fancy devices that can do marker-less AR. Well, with marker-based AR, all you need is a camera. And in most devices, even a few generations back in terms of mobile, have cameras. So that is a good use of marker-based AR. I personally think, as I was just illustrating, that marker-based AR is very, very good for rapid prototyping. Rather than you figuring out really the layout and hard-coding that, or in whatever way you implement the spatial layout and all the UI components, you could also approach this using marker-based AR and then segment the interface, assign different portions of the interface to markers, and then playing around with multiple markers. So multi-marker tracking is a thing, and that's something that I didn't show too much here in this case. But if you were going a little bit deeper on marker-based AR, even we could also do multi-marker tracking. If you're looking at ARJS and Vuforia examples, it does show you exactly how that would work. I also think that marker-based AR is actually valuable for collaborative experiences. Just because multiple people could point their devices at the same marker. And so it establishes a shared coordinate system. So with AR Core, this would be called cloud anchors. So really this idea of sharing the anchors and then enabling the collaborative experience based on this shared coordinate frame. I also wanted to bring back our virtual reality case study. So the zoo, I just really like the zoo. Well, the zoo was obviously designed for VR initially, but here I'm showing a few examples of how we can adapt it to AR as well. So we could take one of the animals and place it on a marker. You have a little giraffe here, and that's pretty cool. So in this case, we always actually have to pay attention that we keep the marker in view. So if you make the object really, really big, like a really big giraffe, if you wanted to have a life-size giraffe appear in front of the user, marker-based AR may not be the best solution unless you have support for extended tracking, so which means that the device can then actually seamlessly switch between marker-based AR and marker-less AR. So here I'm using still marker-based AR. As you can see, the giraffe then obviously, unfortunately, just disappears. And that can be very frustrating for the user, so keep that in mind as you're designing and implementing some of these experiences. But we can actually do marker-based AR, and we can actually bring in more of the zoo. So here's an example where I'll bring back several of the animals. I did leave some out. It was for scale reasons and also for performance reasons, to be honest, because A-frame, so WebXR that I'm using here, actually. Because A-frame, so ARJS that I'm using here, the A-frame version, it's not too many objects you can put in at any one time. This is still pretty cool. I'm going to bring back this zoo, also with markerless. So this zoo, this Detroit Zoo, I won't leave you alone. I'm going to bring it back. I loved Kara's project. I loved Shweta's project. And I think it's great that they both are supporting this MOOC by, helping us learn from their examples. So here I'm doing an almost horizontal to the marker. So that's when it's particularly hard to track. But some of these shots I got in really nicely. And so you feel like, wow, there's a really cool zoo. You can see how the tracking feels a little choppy from time to time. It's a combination of reduced frame rate, just because we're having too many animals we want to show at the same time. And the zoo, in terms of the models, was optimized for VR, not for AR, so it was assuming a more powerful device. And I didn't spend enough time really adapting from VR to AR. I just wanted, as a proof of concept, I wanted to show you how cool is that. We can have that zoo, we can apply our techniques we learned from virtual reality, and we can apply it to AR, and we can do it with marker-based AR. So, this concludes my lecture. I hope you found it interesting and useful. There's more stuff I want to share with you. We're going to look at marker-less AR next. In this lecture, we're going to focus on marker-less AR. So augmented reality without marker, at least fiducials, visible markers. The whole story behind markerless AR is that it's now on the device to find its own markers. And that's something I've talked about in the foundational lectures, in the first course as part of this XR MOOC. And that's something that's going to come back here a little bit. And we're going to learn about markerless AR in terms of frameworks and toolkits based on top of smartphone-based AR. So ARCore and ARKit are some of the examples that we use here. We're also going to use our case study because, well, Shweta actually also implemented a markerless AR version of Kepler's laws. So, and that's what I'm showing you here. So the first thing you need to do is actually decide where you're going to place the content. And even that moving the device initially was very important for the device to do initial plane detection and figuring out a little bit of the environment. And then we have it there. And then you have it, the first law. And we changed a little bit the design here. We have this tabbed interface, and you can actually click these tabs or tap them. And then you can actually switch between the visualizations. So no more paper involved. I'm just using the same table and to show you, to illustrate it to you. And then the interactions are actually here. That's still lean touch. It's still the same. Keep in mind that this actually is the version that we had implemented first before we did marker-based AR. So it's funny when I say it's still the same. But depending on, that's how you perceive the content. So, and I don't think it would have made a big difference had we designed this second. Maybe we would have kept the tabbed interface horizontally, more aligned with the paper or with the tabletop on which we placed the surface on which we placed this. Also, all this stuff is still working. The interactions are very similar, so you can tap to pause this simulation, for example. I just enjoy watching these planets, so you can just tap on screen and that actually pauses. We can learn about this law of equal areas, the second law. My goal was not so much that you actually learn about Kepler's law of planetary motions. It's just a use case. It's a case study for us. We want to learn about AR, just like with the zoo. The zoo was a technological case study for us, and this is a technological case study as well. So the law of harmonies is also interesting, and it's cool how we can actually move multiple, adjust the orbit of multiple of these planets at once. I think that's a cool part of the interface. And because it's markerless, I don't have to pay attention to anything. Well, the surface, to be honest, if I were just using this plain white surface rather than putting things on top of that table, the tracking wouldn't have worked that well. So that's why I it's not that I really wanted to have my notebook there and all that stuff there, but I needed to have some visual features on that white plane, that surface that I'm using here. And I wanted it to look nice for you, so tidy. You see how nicely I've arranged the pens in the background? Yes, so it's all fake, but it is not too far away from what a nice and clean desk could look like. And then, so pay attention to the surface tracking. So a monotone surface or monochromatic surface, like a green screen, would actually be the worst case scenario. And then you can actually, in this case, tracking works pretty well, and I can actually really follow these planets. I just really like how this looks, and it's pretty cool. And so thanks again for that case study, Shweta, that we can actually learn from. So markerless AR. So here we're going to talk about markerless tracking, okay? We still track. So how does it differ from marker-based? What's the magic? We're going to talk about that. We're going to learn about the basic user experience through some examples. So that changes quite a bit. So we need to actually design more digitally now, and cannot offload too much into the marker design. So we need to concern ourselves more with basic user experience. Obviously, you need to do this with both, but as part of this lecture, I can focus more on what happens on screen, so in the world, or on screen on device. And so then we're also going to learn about markerless applications. So really, what are the limitations, or at least the advanced technical requirements when it comes to markerless AR? Are we still reaching the same amount of devices? The answer is no. So compared to marker-based, you're reaching a much smaller subset of the population. But most latest generation smartphones actually support it. So it's pretty good. So markerless tracking, really think of a layered approach, as I say here, to markerless tracking. It's not just plane detection, so not just horizontal and vertical planes as the primary means to represent the environment. No, the environment is much richer. Not just doesn't consist of just planar surfaces. So a more advanced spatial mapping would allow you to really do a 3D mesh reconstruction, including texture mapping in some of the advanced devices like the HoloLens, for example. And then on top of that, that is now also supported by the iPad with LiDAR scene understanding. So actually really doing semantic scene understanding, so allowing you to classify portions of the mesh using semantic labels like a face, walls, floors, tables, seats, windows, ceilings. These are some of the labels that are commonly supported at the moment. And then we can do segmentation based on that. So we can do background foreground extraction, we can do sky extraction, we can actually segment people. That's the thing that I'm going to show here. The sky is something that there are some really impressive demos on the Magic Leap, and then also Snapchat has support for this kind of segmentation. That's markerless tracking, and here I'm going to show you an example of plane detection, just using WebXR. And when I say just using WebXR, to be honest, this is the latest, really just like hot out of the press, the latest Chrome on Android, the latest WebXR, an evolving standard. So it's actually still, the specification is still being written as I'm like designing this MOOC and recording this, so I'm proud that I can show you this. It's not too different from some of the other demos that I'm going to show you, but this is actually a web-based, so using the latest WebXR, bringing ARCore into the browser, and what you can do here is plane detection. And so I visualize the plane detection not by visualizing the plane, but by visualizing actually how that cube would be appearing once I pick the plane. And I thought that's actually a good way to visualize it. Most of the time, in later examples, you would just see the planes visualized like this way. But this is, I mean, while it is relatively useful because I still match the content to the plane, most of the time it will be too abstract. So think a little bit more about whether you could have a preview, like a wireframe or some kind of transparent copy of the content, so that you get a sense for the scale. Because where you detect the plane, similar to marker-based tracking, it would actually determine the size, so the scale of the content, and also constrain a little bit how you can move it inside that plane before you jump to the next plane. So that's something to keep in mind. Here I'm going to show you an example using AR Foundation. So that is now an abstraction in Unity, an abstraction over both ARKit and ARCore. I'm running it on an ARCore phone. I'm going to visualize we're going to visualize the point cloud here. So these are all the little feature points, the key points that we keep tracking. And we can kind of like show the whole point cloud as it builds. So that's like how the device understands the environment. So that is spatial mapping. This is a point cloud. And then we can detect surfaces, so planar surfaces. We can actually approximate it to planes and detect those in the point cloud. And I can also show just like per frame what we see per frame. So rather than the whole point cloud as it is collected over a series of frames, here you just see in each frame, you just see the individual per frame on a frame per frame basis. And you can see how we are refinding some of the points, and sometimes we just can't find those points again. So we're building new features, we're picking new features so that we overall have like a constant number of features that we are tracking, so that we can relatively reliably understand how the device is actually moving through 3D space. So these were some of the more fundamental features. So plane detection and then point cloud, how does it work? Let's talk a little bit more about basic user experience. So the basic user experience example that I have here is this one. It's actually also from AR Foundation. So I compiled it and tried it out. And so it shows these feathered planes down there. And then when you touch the screen, it does the surface detection, and when it works, so when it actually detects the plane, then you can actually place an object there. And the object will appear larger, obviously, if it's like on that plane, and if it's like in the background more. So if it's further away, then it'll appear smaller. I think I was trying to attach it to the screen. And it's a vertical plane. So vertical planes used to be hard. Horizontal planes we had that first, but vertical planes like this one on the TV, that only was introduced later in ARCore and ARKit, but now we have it, and so we can detect both walls and the floor. So and as you can see, everything is still there, and it's actually still spatially like really anchored. So that was the basic user experience. So basic user experience is really like this. Okay, bring out your phone. The app asks you to move a little bit left and right, and that's not just because it wants you to exercise. No, it needs to see more of the space. It needs to be able to do triangulation, so it needs to be able to see a few frames from different angles, slightly different angles. Then we can actually figure out, oh, okay, through triangulation, we can estimate depth, and we can figure out, oh, these points then actually together are like at that distance, so there is a rough surface here. Bam. And that's how this works. So basic UX is like tell the user to move around a little bit. Once the tracking is established, it probably removes that animation that it had initially. We start visualizing the planes. In this case, it was this feathered planes visualization. I like my preview of where Conrad was going to. Oh, I'm biased. I implemented and designed it this way, but I think it's useful. Anyway, and then once the planes are there, then the user can tap. And as the user taps, we can actually do intersection with these planes. So we can actually really understand how that part works. So that was basic user experience. And let's look at how to make it a little bit less basic, no, a little bit more advanced. I'm going to bring in occlusion through the Depth API. Now, the Depth API is a relatively new feature in AR Core. I mean, relatively at the time of the recording. And I'm actually placing objects. Once I enable the Depth API, I'm able to place objects. And these objects will actually, right now, what I don't realize initially as I was giving the demo, I didn't realize that the objects were actually placed. But they were placed on the plane that chair is actually occluding. And so this is the cool part about the Depth API. It does have that understanding, and it automatically applies occlusion rendering to these objects. So then I have to walk around the chair to see more of these objects. I mean, the fun thing about doing AR things is like you get so excited when things feel more like they should feel when you merge the physical and the virtual. So occlusion is a key part. Light estimation would be another key part, but I don't have a good demo there. And I'm just keeping play around here with this. So occlusion works pretty well despite, and there are obviously some issues with that chair. You can see in this, you can see this heat map how the netting of that chair and the back seat side is hard to realize. It's actually supposed to be like a surface. But you can see nicely how it does it generates a heat map here, visualizes how it does the tracking. So heat map, things that are further away are red, and things that are closer are blue. And so dark blue would be really close. And so in some sense, it's an inverse heat map, if you will. And I can enable and disable it in this demo. It's a pretty cool demo, AR Core demo. I didn't implement it. I just ran it. So it's one of the AR Core samples. It's pretty cool. And yeah, I think it's pretty advanced and works actually really well. Now we're going to do even a little bit more advanced user experience. So one thing that is very important is as you interact and walk around with these objects, here we have a spatial mesh as before, but in this case we're using the iPad with LiDAR. And I've done this demo in course 1, but this is now a demo where we can talk a little bit more technically about this because we are in course 3. So what happens is we have a LiDAR inbuilt into the iPad. That's actually pretty exciting. So LiDAR is like a 3D scanner. And then on top of that, we're running actually a mesh classification algorithm. So that is actually coming with ARKit now. And it supports a few basic classification labels like table, seat, window, wall, chair. I mean, not chair, it says seat. So this is actually then finally working here for the window. Some of the previous examples didn't work so well. A black surface table, it's pretty hard to tell whether it's a black surface table or whether it's some shade that we're looking at, some shadow that we're looking at. The glass table is hard. I have too many hard objects in my little studio here. The mouse pad works well, but we don't know what it is. The screen, we have no idea what it is. So it's not really like object recognition. It's really just very basic labels like wall and so it looks cool. I think this is the beginning of this vocabulary of objects that it can detect will grow. especially when paired with a search engine. So that's why I expect more advances from ARCore very soon, which is done by Google. But we are getting there. And this is done on device. That's something to keep in mind. It's done on device, so it actually has the classification built into. The algorithms are run on device, pre-trained. If you wanted to combine it with the search engine, which I think is going to be the next step, just think of Google Lens. And we can detect such a variety of objects, and we have this growing corpus of things. You actually then do it via the cloud. Whether people will be comfortable with that or not, that really has to do with how you think about these vendors and how you think about your privacy and security. In any case, it is useful. I'm going to show you people segmentation. People segmentation is something you can now do with ARKit. I expect very soon that we have a similar solution for ARCore. Probably when you're watching this, it's probably already out. Anyway, so this just came out recently, and actually Shweta helped me with this demo as well. She pre-compiled it and deployed it on the iPad. And then we did like this COVID-19 safe exchange of devices so that I can actually record this in one day and give it back to her. We needed it for a user study. Anyway, so this is pretty cool. What you see here, side story, I know. I do this in normal lectures all the time. So what you see here is how I'm going through this virtual object. There's a virtual vase. It's not real. You can see this by looking at the real world as opposed to through looking at the iPad. And then at some stage, it detects that my hand is closer. So it does people segmentation. And then actually does it really nicely, occludes my hand, then starts occluding the vase. Coming back to our case study, I want to look at the case study again and talk a little bit more about marker-based interactions. Actually marker-less interactions. So these were the ones we had as marker in the marker-based version, and then in the marker-less, they are the same, but they change a little bit how we have implemented them. So we have placing, but not placing the marker, but picking a plane. So that's the first step. So placing means you're moving the device. And we're rendering an indicator. We're rendering an indicator here, a yellow indicator. That's just one way to do it. And then once the user has picked where to place it, then the interface actually appears at this very position. So basically establishing the 3D coordinate system. Then we can start pointing at the coordinate, and it appears the tracking kicks in. The marker-less tracking kicks in. So we don't have to pay attention to keeping anything in view. If we move the device this way or that way, we obviously don't see the virtual content anymore because it is rendered. It's anchored there. It's like fixed in the world, in the real world, and that's how the whole AR experience works. But we can point at it. If I were to point it around the device, so behind the device, let's say I really feel like I want to point into the virtual world with people segmentation, well, which doesn't work on ARCore, but it works on the iPad. If we were to enable this, we could actually point at the virtual content and occlude parts of it with our fingers. I've tried this out. This is not perfect, but it does even work down to the fingers to some extent. So it will require somewhat training and depends how you define the thresholds for the segmentation. But very soon we'll be able to seamlessly interact with the virtual content. We can point at it directly in the physical world and still occlude it perfectly. Tapping, so you can just tap on the content. What you cannot do right now, at least in our implementation, is reach behind the device and do like behind the device interactions, actually tapping. If you did hand tracking, that's something I'll show you more with the HoloLens right now. The current state of implementation, these are all different kinds of technologies that are sometimes available and sometimes not. So ARCore doesn't support hand tracking. And so we had to use lean touch. And so basically doing on-screen, on-device touch interactions, multi-touch interactions. We also have a drag and drop as before. So what does that mean in terms of markerless AR applications? So yes, it is really targeted at more high-end devices. It's not the super high-end. So it's not like, I mean, obviously markerless AR is also what powers the HoloLens. And so that would be very high-end devices. But let's just say relatively high-end, because now you're targeting a smartphone-based generation that is 2017 or later. And yes, most of us upgrade our phones, but not everybody can afford this. So think about that we don't actually, if you're designing a solution and you're picking markerless AR, it does have a significant impact on who you can reach. Also, if you're then looking at WebXR, WebXR is like super experimental right now, and doing marker-based AR is kind of fine, but the interactions work pretty poorly in ARJS with so A-frame based. It's not exactly WebXR, but building on the WebXR specification, we're right now, as I was developing some of my demos, we get hit testing into these now. So we have hit testing in there now, so that we can actually determine when you. I'm going to show you this when you obviously like you have the plane detected and now you want to place the content. You are extending array into the scene from that point on the screen into the scene and detecting where it hits the surface, and this is where the content will appear. This is called hit testing. We covered this raycasting and hit testing in the virtual reality lecture. That applies here as well, and it just applies to the physical world, approximated and represented by virtual planes and surfaces. So yeah, we have basic support for that. And actually rendering content on top of the AR scene. So that's called DOM overlays in WebXR. That requires, it's just experimental. It didn't work. I couldn't implement it nicely. And so I was a bit sad, but in a few months it's going to be available, and you won't even. Had I not talked about it here, you wouldn't even have noticed. So I just dated the lecture, but that's just fine, because if you were expecting to see something cooler than, if you've seen cooler demos recently, I'm showing you the latest stuff I can do right now as I'm recording this. And but the world moves on, and in a few months I expect to be able to do cooler demos even. Still, I would say markerless AR applications, especially when you think about accessibility. Like really, think about it. We can do, especially with a HoloLens, where we have even more advanced spatial AR, not spatial AR, that's actually the wrong term, spatial mapping in these devices. And then we can do semantic scene understanding on top of that, so we can actually understand what we're looking at. That is valuable information that we can give to, for example, people with special needs. If then the main challenge becomes the user experience design. If we figured out the classification and all that and doing it on device rather than offloading to the cloud, again, interesting times. So scene understanding, I think, will be an even more important AR application. Also, that you can actually start annotating things like these common repair scenarios. They're relatively boring from my perspective, but I understand. Yes, so everybody wants to repair things remotely or do telemedicine remotely, and it's always good to have somebody who can give you instructions by sketching into your Vuforia Chalk style sketch or HoloLens remote interactions like Skype. You can then sketch into the world remotely, and then it appears for the user here. So these kinds of that require spatial mapping and scene understanding, I think that's like where you really need markerless AR and some of these advanced techniques. Ultimately, I think right now these techniques will allow you to implement more believable experiences, not realistic. I wouldn't say like we're not actually there yet that we can actually really blend the world seamlessly, the virtual and the physical world. We can make it believable. Occlusion rendering, as I was showing in some of the examples, is key to that, and then light estimation, which I had an example from AR Core in the Foundations lecture, so as part of the first course in this XRMOOC specialization. But yeah, so that light estimation stuff isn't really well used yet in current applications. If it is more used, then we will actually have more believable experience. So less to do when it comes to the suspension of disbelief. All right, as before, I'm going to bring back our zoo. I just love that zoo. So we learned a lot about AR through Kepler's laws, but here is the zoo again. So we can actually learn, we can actually apply the things we've learned for VR also to markerless AR. So you could bring in one animal like this giraffe, and if you compare this to the marker-based experience, now I can actually have a life size, a room size. Here it is. I mean, it's not high poly. This is actually done with Google Blocks, and it's done by Poly. It's like on Poly, you can get this giraffe. It's for free. It's public domain. That's why I'm allowed to show it here. And you can actually place it there. And yeah, it's pretty cool. You can go closer. If this were more detailed content, it would be nicer. Obviously, you could explore high polygon stuff, so you could actually look at it in more detail. And my giraffe is pretty simple, the one that we have here. But this is pretty cool. And we can, and now this is going to be fun. I wanted to show you this, okay? So with this one, I was really going on the floor, and I was bringing back all the animals. And I'm going down onto the zoo. Here we go. And you see some of the animals, how they're like really, well, really, you see some issues with the tracking, like when you're having content of this size, content that size, but the scale is still pretty big, right? I'm almost filling the entire room. But so the tracking isn't perfect. It doesn't seem as stable. If I were to run this whole thing on the HoloLens, it would work even better. And I must say, obviously, some of the lighting conditions weren't probably ideal for ARCore. But that's what I mean. Not realistic, at least not photorealistic, but believable, at least to some extent meaningful. And I could really explore this zoo. Now I could, in my mind, develop this mental model of where these animals are in the virtual reality zoo. And then I was, since I didn't change the spatial layout, I knew roughly what that means for how this maps onto the physical world here. And it's just a fun experience. And obviously, having some key animals like these giraffes and zebras, they really are, because they are so visible, they're like visual cues. They really help the user orient, and that's something you could build into your own experiences as well as you're designing something. So yes, so that is now my markerless AR version, and we even revisited some of the elements from the VR portion. So keep in mind, so hit testing and ray casting really still plays a role. All the things you've learned about basic 3D scenes, geometry, mesh, all the things we did in the first week, the things we did in the second week focused on VR, still you need to carry this with you, because then it's easier for you to learn about AR. And we learned about marker-based and markerless AR. So these things all kind of relate to each other. And in the end, that's when it comes to really making thoughtful decisions. Now you have a relatively complete toolbox. One thing we're going to look at is marker-less AR, and then comparing actually handheld versus head-worn. So we're going to look a little bit more at the HoloLens, the super high-end, if you will, range of devices. I have a lecture on that. I wanted to cover that as well. But yeah, with this, there's a lot of things you can do in the honors track. So take a look at that if you wanted to learn more about how to implement marker-based, marker-less AR. And now would be a good time to check out that content. I really make it hopefully accessible, sharing projects with you and trying to maintain it so that you can do things with Unity and with WebXR. And that's going to be a challenge to actually maintain that over the next few months and if not years. So let's see how that goes. Yes, so I'll see you in the next segment. In this lecture, we're going to talk about handheld versus head-worn AR. So for the 1% of you out there that have access to a device like the HoloLens 2, I thought we should also cover a little bit, markerless AR and taking that knowledge into a head-worn AR display like the HoloLens. One thing that you should always keep in mind, even though all my examples are HoloLens based, there are also cardboard-like solutions for AR, like the HoloKit that I have here, where the phone goes inside there. I'm not actually running it, I'm just showing how this would work. It goes in there, the camera needs to be exposed, and then the screen actually has to do a stereoscopic rendering, so like a rendering for each eye. Kind of like what you would do in VR. But all the black that you render on the screen will obviously not be visible to the user as they're looking through this. So everything that's black here, it doesn't actually appear on the visor. So that's the way to do it, okay? So you're rendering a stereoscopic view for the HoloKit, but you're using at the same time the camera that's up here, using that camera to do some of the tracking that we talked about. You can do marker-based or markerless AR. Cool. So keep that in mind. don't be sad that you don't have access to a HoloLens if you don't have access to a HoloLens. That's totally fine. I don't assume, due to the issues with equity that are real, I don't assume that everybody has access to head-worn AR. But I just showed you how you can do it. Okay, so HoloKit is a cardboard-like, so cardboard like virtual reality cardboard, a cardboard-like AR experience. So this lecture is actually structured around a number of demos. We're going to jump right in. We're going to go onto the HoloLens, and I had a little bit of fun here, so I'm going to show you lots of examples, and then we're going to learn about the differences between handheld and head-worn AR. So let's enjoy this a little bit together. So here you see a mixed reality toolkit example, basic user experience. One of their examples is on tooltips, and you can explore kind of like objects that way. And I'm showing you from time to time the outside perspective, while this is the first person view, which is pretty cool. This is what it looked like for me. And I was trying to, they have some stabilization built in for some of these video recordings. But I was also trying to move quickly rather than going like Jason Bourne style, super immersive, going crazy. I was trying to keep things a little stable for you so you see better what's going on. And so here I'm just playing with some of their hand interactions. In fact, hand interactions is something that we'll explore a little bit more in depth in this lecture. So there's a lot of stuff you can do. Basic user experience. You can have tooltips that can be triggered based on near and far manipulation. So that's something that we're going to learn about. One of the latest examples that I actually liked a lot is the hand menu that I'm going to show you here. So on the HoloLens 2, you now have the hand menu in Mixed Reality Toolkit. It doesn't always work. Like for some reason, it didn't always work well for me. So I'm going to show you the portions where it did work very well for me, so that you get a sense. Sometimes it wasn't triggered. I can't explain why. But here it actually does work relatively well. So obviously it has fully articulated finger tracking, but in this case we're just like trying to get a sense for actually the wrist. Where's the wrist of the user? In this case I'm not rendering the spatial mesh of the hand, and this is what it would look like, the more final user experience, the more polished user experience when you have the menu appear next to the user. I mean, from the outside it does look a little funny how I'm like staring at my hands. And it's still mid-air, right? You're interacting next to the hand. Where I'm showing you again, enabling some of these debugging tools. I'm going to show you a medium-sized version in a second. So you can also see a little bit of an offset between the virtually represented hand. That offset is not how I see it when I run this demo on the HoloLens. That offset really has to do with how this demo is recorded. They're not correcting automatically for the offset between where the camera is placed and how the video is being recorded. But there are also fixes for that. I just actually, to be honest, couldn't figure out how to do that. There is a little bit of documentation on that. And here I'm showing a medium-size hand menu. So hand menus are cool, I think. Manipulation changes. Okay, so you don't have a touchscreen anymore. You noticed this already, but obviously this demo is going to make it very clear to you. So you have to think really about how the interactions change in this kind of head-worn AR. You can do more with speech. I think people will find it more intuitive to use voice-based or speech-based interactions, because it's kind of like hands-free, and so wearing something on your head so you feel like talking to the computer would be fine. Here I show a little bit, actually I show a lot of different gestures. So they have different types of manipulation styles, HoloLens 2 style, HoloLens 1 style. You can go through these examples. I built this Mixed Reality Toolkit 2.4 example scene of their hand interactions. And this is actually the box styles that they have. And I can do, again, far. This is far manipulation using the lasers that are coming out of my hands. I'm Spider-Man. So not webs, but lasers. So the difference is in terms of how near and far manipulation works. is that you need to use more of the anchor points to visualize it to users what they're actually grabbing, which part of the which part of the object they're actually grabbing, and what kind of transformation they're actually executing. Now you can do really cool things. Like I like this example of the clipping planes, and these clipping planes can come in different form and shape. And now it's actually using a feature of the HoloLens, a feature, the feature that we cannot render black, and it looked a little different. Actually, for most of my demos, when you see something black in the video, that is actually transparent to me. I don't see it. It's because of how the display technology works, I don't see it. And so this video capture is not exactly the user experience, but it comes very close. It feels like a really nice see-through cube that I'm holding there. And I'm going to come back to that issue later as I'm going to show you one really, really cool experience, Mission AR, that is actually an Unreal experience. So done with Unreal, but it's an Unreal experience as well. It's pretty cool. So let's explore handheld versus head-worn AR. So first of all, here's my handheld. So handheld, varying display sizes, right? Can be smartphone, can be tablet. We usually have a mix of 2D and 3D content, and then primarily touch interaction. Obviously, you can do voice. I mean, you could do whatever, but the primary ways of interacting is actually through touch. 2D screen and touch, 3D world and touch, so where you place content, so content placement, and device motion gestures. So what I mean by that, obviously, since we can track the device, this is something I explored in my XR Director research project, we can use it for puppeteering. So I can actually move objects just like by moving the phone. I move an object, a virtual object that is associated with like an airplane. That was always one of my favorite examples. And now I was able to demonstrate it to you. So device motion gestures. Keep in mind that we can't move the device too quickly because we still need to do tracking, and tracking, while relatively robust, is not that robust. And voice commands. So, and then obviously when it comes to handheld, we can do marker-based or markerless. I mean, it's also the same for head-worn, but for head-worn, I would say markerless is more popular. So marker-based tracking, markerless tracking, extended tracking, so this transition, for example, supported by Vuforia, using the marker initially to establish the coordinate frame, and then switching over seamlessly to markerless tracking as you're moving the marker out of view, or just for other reasons loses tracking, like you're occluding the marker. If you're looking at it from the head-worn AR side, so we usually have a very small display. So the field of view, right? The field of view. You would think that when I put this on my head, and this is part of my foundations lectures as well in the first MOOC, you would probably think that, wow, everything is super augmented for me now. But it's actually like these are the portions that are augmented. Everything else around it is just the real world. And I have peripheral vision, not just the foveal area. I actually have peripheral vision. And so that can be disappointing, even with the HoloLens 2. So I'm going to show you, not like the field of view in a virtual reality headset, where we have 120 or more degrees of the field of view, where we can as an occluded display. So we're shutting off the real world, and everything else in there is actually black. That's why we have all this stuff here to really control nicely. And so it feels like, wow, such a better view, so much more augmented view. And so that's something to design for. And that's something I'll cover in our XR research lecture, where I'll go in a little bit in more depth about one of our research projects around the mixed reality toolkit that we used to develop an analytics toolkit, and then also design a crisis simulation case study. Well, the field of view was really a limiting factor. You actually have a heads-up display or 3D content, right? There's no more 2D display. I mean, there's nothing you can touch. I mean, you don't reach into between you and the glasses, the goggles. The interaction, I mean, Google Glass had these things on the side. They could actually touch things on the side. The HoloLens doesn't have any of this. at least not released. Maybe there are some sensors inbuilt. I mean, you could do a little bit of IMU detection, and I mean, I'm sure you can read that signal. And so that's like how, for example, pass-through works on the Oculus Quest, which I think is there. So yeah, that's but so there is a heads-up display. That's what you can do, or it's so that sticks with me, or it's like placed in the world, and then basically when I look this way, I don't see it anymore. Actually, at this angle, I would already not see it anymore because of the small field of view. And you don't reach into the display to do any interactions. All the interactions happen in front of the display. That's why we have these cameras. So this is outside-in tracking. Sorry. So this is inside-out tracking, not outside-in tracking. And so basically, the hands need to be in front of the display in some area so they can be tracked. So that's important. So we can do gesture. We have a heads-up display. We can do 3D content. So you can do hand and voice. And I say hand because I'm assuming we're talking about HoloLens 2. That's more like the latest. And so we can do hand and finger tracking. So we can do finger-based interactions as well. We also can do eye tracking. And so that's something that on both, I don't think I've covered it sufficiently, but eye tracking can be used also for interactions. And I haven't seen a lot of useful examples yet other than scrolling with your eyes, which I think is interesting. So head and eye gaze and voice commands. And so I would say when it comes to tracking, when you're designing for devices, these high-end devices, you actually have access to advanced tracking. So you have inside-out, 6 degrees of freedom tracking. Spatial mapping, it just comes for free kind of. It's built in, especially when you have like multiple cameras like the HoloLens, including a depth camera. It's like a little Kinect on your head. And then we have scene understanding. So advanced tracking with scene understanding. That's like, can do so much with it. If it's well done, we can do so much with it. And so this will be, and some of these technologies, it's interesting. And so people have argued that the smartphone-based AR was just to figure out how to design better head-worn AR. So all the features that you get in one of these platforms, and right now it's still a little fragmented because there are different technical requirements in order to, for example, do really reliable spatial mapping and scene understanding. So doing it in software, like with ARCore and ARKit, so visual inertial odometry, that was actually really a key enabling step. Previously, you always had to rely on depth cameras. So if you've heard of Google Tango, that was an exploration by Google of how to augment smartphones with depth cameras. I really like that project, and I really like Johnny Lee's work, but it kind of was superseded by ARCore, and Johnny Lee is still pretty involved, I'm sure. I'm going to show you one example here of my cube examples are back, and I really like this one. I have shown you a little preview of this before, and I want you to actually listen in as I go through this demo. So enjoy. So what we're going to do is I have a virtual plane of cubes in front of me. These cubes react to far manipulation and also near manipulation. So I can actually go in there and grab one. And they react to physics too. So this one I'm now going to just like put on my little table there. And as you can see, it is now sitting on this physical table. And I've supported this glass table with this white poster board. So it's a little bit of a trick there, right? This one, let's see whether we can actually place it in my shelf. You coming with me? Yes, okay. So we're going to try to place you here. This is where normally the HoloLens 2 sits, but we put this cube there. And this one I'm going to do far manipulation. I'm going to grab it. And I'm going to just like let it fall here. Let's see what happens. Boing. And it's on the floor. And at the moment, it doesn't really detect the seat as an obstacle, so it doesn't do the occlusion rendering. I'm going to grab it one more time. And we're going to place you here on the table. And this one is below the table, so you can see how there is occlusion between the two. So one is on the floor and one is on the table. And also if I take this and just like drop it here, bing, it'll be on the floor next to the other one. And then I actually have fire manipulation. It's just a little tricky, it's a little sensitive. Overall, definitely quite cool. I'm going to place you back here on the virtual shelf. This is where we started, and that's it. Huh? That's what I'm talking about. Now all these technologies are coming together. We have spatial mapping, we can bring in physics, and we have near and far manipulation, and so it starts to feel like I'm interacting with this virtual world in an intuitive and a natural, as they say, instinctive interactions rather than natural interactions. So that's beyond natural. Sorry, I'm not making fun of this. It's just a little. Anyway, if you're a human-computer interaction researcher like myself, you get it. You would find this funny, potentially. Anyway, so near versus far manipulation we have just explored. And there were two examples here. One was where I was taking this cube and putting it into the red shelf. So that is an example of near manipulation. My hand is really inside the object. And here on the right, you see far manipulation. So lasers coming out, or spider webs coming out of my hands. And that is changes, obviously, reach. So I don't have to go there. I don't have to teleport. So there's no teleportation in AR. It doesn't actually work well in AR. Teleportation would be very confusing. This far manipulation is a workaround, and it works actually quite well. I don't have to run over there to get the cube, and so this is really cool. So let's look at what are the head-worn AR applications. So in terms of reach, so this is really very high-end devices, unless you're doing something like I said initially with something like this something like this AR-based cardboard. Or cardboard for AR called HoloKit, where we can still use our smartphones. You were talking about high-end devices like the HoloLens 2, where I'm sitting right now is one of the high-end devices. It's very expensive and it has a lot of cool features that are in some ways breakthroughs, just nicely put together in this device. But not a lot of people have access to it, unless you're working in enterprise context. Obviously, I understand if we're talking money, then yes, you have access to it. And I could have designed a different MOOC. I could have designed a masterclass because, to be honest, in my research and my work, I do a lot of stuff for some of these high-end devices. I don't do so much smartphone-based AR. But I still think, like, if you're targeting classroom scenarios, which is one of my roles at Michigan as part of the EXA initiative, I work on a lot of these projects, or at least consult on them. We're doing a lot of smartphone-based AR. From a research perspective, smartphone-based AR is so yesterday. In research, we are like 5 years ahead. Usually, at least we try. Depends how you want to do the impact. So that's a little bit of a preview of my XR research lecture. Hope to see you there. So we're talking about very high-end devices, direct manipulation. So really, like, it feels really natural. Like I was, especially the near manipulation aspects, like you're really grabbing into the content and then you're like moving it around. You have to do a gesture like this. At least that's how it works right now. I think we can support more intuitive interactions in the future as well. People would want to do all kinds of things. It doesn't always work like I'm doing all these gestures here super fast. This is how you wished it worked. But it's still not really Minority Report at the moment. And so, but we do have support for direct manipulation. So rather than through a touchscreen, which we also call kind of direct manipulation, but it's still actually when you then have content in the world, if you think about it, right? Direct manipulation on touch on the screen, I understand, makes sense when you move objects around. But you're actually interacting with content that's spatially actually over there. It's just rendered on your screen. And so is this still really direct manipulation? Direct manipulation really in the sense of head-worn AR, you can go to the location, pick it up. So that kind of using your hands and interacting with the content directly. That's what I mean here. And then multi-modal interaction. So combining gesture and speech, for example, or different kinds of interaction modalities. Gesture and speech would be a way to increase reliability. So password entry through gesture or speech is something not so good. But if you combine some of these modalities, obviously you make it harder to have false positives. And that would be a better way, a more reliable way, especially when we're targeting accessibility applications. Then multimodal interactions could make a lot of sense. And yeah, so that's what I wanted to talk about. We're going to come and we're going to watch a little bit of, I have this as a separate video for you. It was so cool to do this. So please, when you feel like, please watch this. This is really, you should watch this in full screen, get some popcorn, watch the Mission AR Unreal example. It's one of the coolest things that is currently possible with Unreal and the HoloLens 2. It is really a nice example. I have that video separately for you. And yeah, anyway, so please watch that and learn more about, if you're excited about markerless AR, and then if you're excited about head-worn AR, then I think now you have all the building blocks to do some of these more advanced things as well. I'm glad we covered all this. And well, look forward to seeing you in the Honors track. In the Honors track, I don't actually have specific content targeted at head-worn AR. I thought it wouldn't reach enough people, but I'm happy to add more content. I mean, we have so much stuff going on in that space. I could provide more examples with MRTK on HoloLens. So just let us know. So thanks for watching this.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
The Saturn V was a three-stage rocket. Each stage had a part to play to make the journey from the Earth to the moon possible. When you're ready to see how it all worked, touch the glowing base of the Saturn V to initiate the launch sequence.
Ignition sequence starts. All engine running. Liftoff. We have a liftoff. Tower cleared.
Reporting the roll and pitch program, which puts Apollo 11 on a proper heading now.
The third stage fired once to get Apollo 11 into a parking orbit around the Earth, and after a few hours for system checks, fired again to send it on its way to the moon. Ready to move on? Just press the glowing command module.
Apollo 11, this is Houston. Your go for separation.
As the lunar module was designed to fly in the vacuum of space, there was no need for it to be aerodynamic. Weight was kept to an absolute minimum. The walls of the cabin were no thicker than a few sheets of aluminum foil. The astronauts didn't even have seats and piloted the ship standing upright in what was essentially a controlled fall from orbit. When you're ready to proceed, press the hatch on the Eagle. Seven hours later, the commander made his way down the ladder to stand upon the foot of the lunar module.
Okay, we can see you coming down the ladder now. Okay.
The combined 360-pound weight of the commander and his spacesuit was a mere 60 pounds in the 1/6 gravity of the moon, making movement extremely easy. All that remained to do was for the commander to take one small step for man, one giant leap for mankind, onto the surface of the moon. This footprint represents the culmination of a decade's work by almost 400,000 people in what was one of the greatest periods of discovery in human history, and is still probably there to this day. Press the footprint when you are ready to end this demo and return to planet Earth.
Hello and welcome to this video on marker-based AR experiences in WebXR. Specifically, we're going to use A-Frame and have a few examples of markers here. The hero marker that you've seen before. I also put like a kanji marker up like this, or a cutout like that. Or I also have like these little markers that I can just like hold. And so I'm kind of feel like I'm well prepared to show you a few examples of using marker-based AR. And I have a webcam set up and I have a few examples prepared for us. So we're going to do single marker tracking, multi-marker tracking. Going to show you how to bring in a little bit more of a VR world into marker-based AR. We're going to do the Hello World AR, and well, Hello World in A-Frame, but for AR. And I'm also going to talk a little bit about interactions and some of the challenges you will have there. Throughout this little demonstration, I have shown you in the first steps how to get it to run on the phone. So each of these examples will actually run on the phone, but I'm not going to actually, well, maybe I'll do it sometimes, we'll see. I'm not going to put the GoPro on now. I feel like that would be a little bit too much. So here are my slides, and so one of the things we're aiming for, or something that I've shown before, is this scene where we can see the giraffe as like one of the elements from the zoo case study on a marker, a hero marker here. And that's something we're going to recreate also as well in this little session. So when I think in terms of XR experiences, then when it comes to marker-based AR, content-wise, usually just a 3D model that we look at, maybe a little bit of animations, lights and shadows, maybe, menus and HUDs, maybe. Mostly it's really just looking at a 3D model, not even too much going on in that 3D model. Sometimes, as I say, a little bit of animation. When it comes to interactions, it is mostly cursor-based. Obviously, we don't have a controller. Voice and speech are very uncommon, and though actually possible. And on the implicit interaction side, a lot of it might be location-based, but obviously marker-based, so fiducial. So I showed you lots of examples. This is the kanji one. This is the hero one. These are some of the most prominent ones when it comes to ARJS. Most of my examples will probably just involve the hero marker. You print them out usually. So that's what you should do. You can actually display it on a computer. So you could actually display it on the monitor. That's something you could do. And I have shown that in the first steps as well. So ARJS is really this marker base. So basically when you see a marker and bring your phone into view, then it would show like this marker when it runs an ARJS scene. It would show some kind of whatever the virtual content is that you define inside that marker. So ARJS here has a little bit of a new website now, some examples. So feel free to look this up. Tells you how to embed it. I haven't played much with these other modes. For me, ARJS was always just marker based. I don't actually really understand the differences between image tracking and location based. And then you have an A-marker tag, and that has various options, and you can use it with Three.js, so directly on top of Three.js, or going the A-Frame route, which is what we're going to do. So that's the documentation, and then this is what the marker looks like. So you could print this out. I'll provide a PDF of that, or I link you to it where you can find the marker. And here's our first example. So I have this ARJS template. So I'm going to actually like open this again just so you believe me. So it's here. It's already working. So basically, I have the webcam set up here. It's looking down there on the marker, and it's shaking a little bit when I move, but that's just how it is. And now I can actually interact with the marker, move the marker around, do all these things, and the tracking is relatively robust. Again, if you occlude the marker, or if you kind of like bend it so that only half of it is visible, then it wouldn't work. But as soon as the full marker is in view, it kind of works. Sometimes I have a autofocus problem here. I do have lots of these markers. I've printed out quite a few because I usually go to lectures, and this is one of my nicer ones, but here are lots of markers. I'm just going to place them there, and so they all work, and when they are detected, usually just one of them, so then it finds the orientation. Camera is a little confused because I like go in with my hand, it tries to refocus, but now we want the attention. So one marker at a time per default, okay? So that's the ARJS template, feel free to use it. I do have a little bit more of a project prepared for us. So we are actually going to work in my glitch project. I have an ARJS, well, folder. I was just playing around with a few things in here, but ARJS index is our starting point. And so that starting point is actually exactly the same contents that we have in the template. So you bring the marker into view and ta-da, okay? So let's look at the code. So for that, all I'm doing is getting A-frame ARJS, and then this is kind of more or less required, so that one of the issues you may have is that the marker, so if the marker, which right now is really a box of scale 1:1, red, and a little bit 0.5 high, I can explain why that is, so that we are actually sticking on top of the marker. So the 0, 0, 0 of the world now is really like in the middle here, and so that's something to remember. 0, 0, 0 is there. So if I actually place, if I put it at 0, 0, 0, then that's what it would look like. So you can now see it's kind of like this. So you want it to be on top of the marker, so you push it up along the Y. And if you wanted it floating, then you could put it at 1. So then it would be like floating a little bit above the marker. It doesn't look good actually. Usually like this gap doesn't look so good. So what I'll do usually is just like I take half of this Y scale, so that's the scale per default is 111. So that would be that. Reloading, and it'll sit on there nicely. What you could also see is I actually have a plane here for which I have linked the hero marker. So that's just like something I've uploaded to this glitch project in my assets. So here's the hero marker. Just so that we have a little bit of feedback regarding tracking. So, and I can show this or not. Now I'm going to just show you the plane. And so this is something I've shown in a previous video, but this is just like to show you how well the marker tracking actually works. It gets the pose really relatively right. It's just planar, so just like a planar surface. So what I mean by this, if I bend the marker, it won't work. In fact, it stops the tracking. So something to keep in mind. And then, so I'm going to just get my object back, and we can just like hide this plane down here. So in this case, we just have really the marker, but don't show anything for the marker, and then just have the virtual content on top. Okay, so one of the things I wanted to show you is the hello world. Okay, so how would we, and I'm going to actually do it rather than just copy paste. So I can actually change obviously the content in here. Let's just get this plane back, but instead of this box, we are going to be like inside this marker. Okay, that's maybe also something to say. So you're defining this marker, a marker, which is preset hero. And if I wanted to, I'm going to just bring the content back. I could change this to a different preset. So right now it's hero, but if I change it to kanji, then it wouldn't actually show anything anymore unless I bring in the kanji marker. So once I bring in the kanji marker, so now it uses this pattern, this kanji pattern, instead of the hero pattern. So the question would then of course be, how does it work with multiple markers? And I'll get to that. I'm going to go back to hero, and we're going to get the A-frame AR scene. So we're just going to go to A-frame IO. Not now. I just want to go there, show the source, and grab the code for just the hello world, so the typical. And one of the things I wanted to see is how big it actually is. So this is our A-frame scene, the way it usually is defined. Just so you remember, this is what it looks like. Okay. So, and now this is obviously the typical cube, sphere, cylinder, plane. So if I now bring this into our scene instead of the box, what do you think is going to happen? Well, trust me, it's going to look pretty weird and big. And why is that? So, okay, first thing I could do is, well, I could adjust the camera a little bit. So I'm going to move the camera. I actually don't want to move the camera. What I'm going to do is I'm going to use a slightly different marker, so different marker size. I'm going to remove the big one. So let's lose this small marker for now. So really the issue is the scale, okay? Also, if you think about how VR works, we usually assume the camera will be at 0, 0, 0, so like where the webcam is right now. And then we're pushing the scene -3 out. But the scale is automatically the scale of the marker. It's normalized by the scale of the marker. So the best thing to do is actually put this entire world, I mean, it's not too big a world, into an entity, and then scale it down. So 1/4 of the size. And so let's see what that looks like. Now it's cute, right? And if we're doing, that would almost fit, okay? And now we're going to push it a little bit along the z-axis. And so we're going to do position, and it's probably, so this is -3 out, so we're just going to do 0, 0, and then we're going to actually get it towards us. So that's like half marker size down. That didn't work, so I'm going to do just the whole thing. And that's kind of how we want it. I mean, this is now my baby hello world, and it's kind of cool. It has the shadow and everything. I like it. And I'm going to bring back the bigger marker just so you see. Bigger marker, bigger world. Okay? Really small, big, small, big. Tracking is always better with a bigger marker, but maybe you don't want it to be that big. So we've done that. That would be my hello world example. And then I also wanted to do interaction. So the hello world example is really my example of showing you a little bit more complex, let's say, okay? Because you have like 3 things in here. Obviously, maybe you think more complex means models. I'm going to get there. We're going to get to the giraffe, okay? I do want to do interactions. I think it is pretty key. And interactions with models are a little tricky, and I talked about colliders and all these kinds of things in the VR, in the VR hands-on videos. So here I'm just going to focus on the marker-based AR interactions and keep it relatively simple. So we're going to get actually a red box. So color is red, and position is 0, 0, 5, 0. Scale is default. I'm bringing back our plane. It's red, so that's what it's going to look like. Ta-da, bam. Maybe make it see-through opacity. So add opacity so that you can actually see the world behind it. Usually do 0.8 or 0.5 or something like this. So ta-da, that's what we had before. And now, what you've learned is obviously we can use the ray origin, so we can use a cursor on the scene. That's something I've shown you before. So cursor, ray origin, mouse, and then we could do a little bit of JavaScript. I'm going to show you. Previously, I've done the event set component. In this example, I'm going to actually do a little bit of JavaScript down here. And we're going to have our function, change color, okay, and then that's going to call, let's call element, and then HTML, set attribute color color, and we're going to do we're going to take two parameters here, change color is our function, and then we're going to have on mouse enter, and that is change color this, and then, well, let's make it blue, so as we enter, and then as we exit, make it back to red, leave, mouse leave, on mouse leave. So the question is now, why does this not work? And that's because there are issues with this ray origin cursor thingy, and also mouse enter, mouse leave should actually work. Let's see that we have a little bit of debug information here. Yeah, so no errors there. Mouse enter, mouse leave. Maybe that's not exactly the right thing. So what we're going to do is we're going to call this. We're going to give this an ID. Going to call it box, and then box set attribute. Add event listener. Okay, and then mouse enter. We're gonna just do something like this. Actually, we're gonna change color of this to blue. Okay, and then when we exit, so mouse leave, we're gonna make it red again. So let's see that that works. Still not. And I'm just like cursor, ray origin, mouse on scene. Doesn't work so well. The issue is that is actually a bug in A-Frame ARJS. So what you should do instead is actually go into the camera here, give it look controls, maybe, that's for debugging maybe, and then we're going to have a cursor here, and that cursor now actually should do the trick. So having a cursor in the scene, so now I bring the object into the scene, and that now does the interaction. Okay, what I'm simulating here is actually moving the device, but I'm moving the marker. So keep that in mind. The ray origin, what I had before, works normally well, but there is a bug in A-Frame ARJS, and so you kind of like have to work with the controller, with the cursor here. And I did the look controls so I could bring things into view for debugging, but it obviously messes up the experience. So I'm going to actually remove that. And the way you could debug this is like when you take this and bring it into the view, and then as soon as the cursor enters, the object becomes blue, and then as it leaves the object becomes red. Okay, so that's that. And so we have a little bit of basic interactions with mouse enter, mouse leave, and maybe in the next video I'm going to show you how to actually develop a component that does something like that. We have done it via attributes, so event set attribute, which is actually event set component, which is actually a component. And now we've done it via JavaScript. I'm just wondering whether, I'm just going to do this, what I had initially. I'm just curious whether that would have worked, because I mean, maybe there's something different about this. So mouse enter and mouse leave should actually do the same. It should actually bind it to the element, and this is not good style. Okay, that's maybe one thing to say, but if it works, who cares? And it does work. Okay, but still, I'd rather you not do it this way and do it in a nice way. And maybe even better would be we define the box as, and actually get element by ID and then box. That would be the nice way to do it. And then this one I'll just X out. So this wouldn't work anymore. But we still have the functionality working because I have the JavaScript functions now properly bind, and I actually selected the object via query selector. So we can actually make this a const because this will always be our box. And a better practice even would be to call this box element. So if you're using jQuery, and then I always think it's better to call things that are really the DOM element L. So scene L, camera L, box L, and this would be the best way to do it. Now, per definition, or per browser, let's say, in most browsers, what happens if you name an element with this ID box, it would automatically become available under window.box, and so you just writing box would refer to this element, but not a nice way to do it. So we've done interactions, so can tick this off, and we are going to get our little giraffe back. Okay, so let us, I'm just gonna copy this as another example in here, index to HTML. Just gonna copy that there, so we have that there, and you can see how I did it. In the original solution, I've used the event set, so it's just using the A-frame event set component. That's kind of nice because all you have to do is this, and put the cursor in here. So if I call interactions, here interactions, that would be, I've done it a little bit differently. I did mouse down, mouse up. So you bringing it in doesn't actually trigger the interaction yet. You have to then click down, up, and that would be theoretically that would be here on the phone. I'm just gonna remove the marker for a second and go to the phone. See that I'll show you what this scene now looks like. So I'm just going to open it on Chrome, and I'm going to XRMook, GlitchMe, AirJS, that's where I have it, and then interactions. And obviously I'll be sad if it doesn't work, but nobody knows. So here is the phone. Okay, so I'm going to rotate. Okay, now I'm going to bring the marker into view. We're going to see the marker, and now me clicking, oops, okay, so now me clicking actually triggers the event. So I'm going to put it a little bit further away. You see how I'm using the cursor and tapping. So I hope you believe me that this kind of works. All right. And having this cursor is actually not the worst of things, because you know what you're pointing at, and sometimes it's really difficult. So if I'm pointing somewhere else and I'm clicking this, it won't trigger it. The cursor that you see here in this example right now, ignore that. I'm going to just go here again. We also have the cursor there. Okay, hang on. I'm going to just remove the cursor so that's not so confusing. You're seeing too many cursors, I feel. Okay, so reloading, no cursor anymore. And now we just see kind of like what's on the screen, and me clicking triggers the action. I realize the webcam resolution isn't very high, so I'm going to actually do a quick screen capture. So here's my example scene. I see the cube, and I bring it into view, and I click, and that then actually triggers the interaction. And if I'm not on the object with the cursor, nothing will happen. So only when I'm there. Okay, so this one is a version where it requires mouse down, mouse up, which is the same as clicking. You could also write pointer down, pointer up, which is more neutral. Could also use touch down, touch up on the smartphone, but then it would only work on the smartphone. So the cool thing about these interactions is that they kind of like generalize, and I find that pretty cool. And so that was just this running this quickly on the smartphone. And I'm also going to show it here one more time. So going to bring it up one more time, rotate it nicely, bring it into view. So now we're going to see it on my smartphone. I see the object and I click, and then obviously me moving would work still, and now it feels like, oh, AR, and I point at the object and I click, and that then triggers the interaction. Oops, I was accidentally hiding it. So that kind of works, and that's my interactions example. Okay, we're getting there. And giraffe time. Okay, giraffe time. So we are getting the giraffe. So for the giraffe, I have I'm going to get Google polyload component. So I have a single marker example. So from that one, I'm just going to get the Google marker, the Google polyload. So we need that so that we can load our giraffe, and then instead of the box, so I'm going to remove that script. We don't need that change color script for now. And we have the hero. Instead of this box, we are going to get the giraffe. So I have that in single. I have it prepared. So this is our giraffe. Okay, just copy paste it in here. So I'm not doing anything else other than like rotating it correctly, giving it the scale. And you know what? What I'm also going to do is I'm going to get the animation from the VR scene. So our basic VR scene had like the spotlight and everything, and we had the cool animation here. I'm going to get that. So put that in here, index, here in this one, this one, get my animation, and let's reload. Now we have the giraffe there, and it's moving. It's a bit big. Okay. Well, you know the deal. You can do a smaller marker. And it's moving. So, like seeing an object in AR, it's the same one we had in VR before, but just like seeing a little bit of an animation there is kind of super cool, right? It actually does add quite a bit. And I do like how I'm just with a simple rotation. I mean, there's nothing fancy about that. It's just simple rotation over 2.5 seconds. And that's something we played around with the VR scene. So what I'm going to do now is going to do multi-marker tracking. So I have an example for that. This is this one, ARJS multi. And I'm actually going to copy from there. We don't actually need to copy from there. So what I'm going to do is just take the whole thing, duplicate, make it a kanji marker. So I'm going to get a kanji marker. My second giraffe, and the hero over the kanji would look weird, so that's why I'm removing that plane. And in fact, I'm actually going to remove it here too. And so I'll reload. Oh, there's one thing. It will not work yet, but I'll reload. So I have like, gonna have hero and kanji. So gonna get hero and kanji. And now it works on the kanji. Oh, it does work with marker? Oh, they changed that. I didn't know that it can, per default, now do multi-marker tracking. Unless I have just like this. Normally, it used to be that you had to specifically specify a mode, but apparently this works now. I think they changed that. So in old versions of ARJS, I had to change the matrix view mode. Okay, so then Okay, you don't have to worry about it. Okay, so you're just bringing in two presets. We have two markers in our scene now. I'm going to show a little bit. This is actually the multi that we're working on. I'm going to hide a few things. All right, so then we have the giraffe. So one of the issues now is like they're actually moving the exact same way, okay? So, and they are too big. So we're going to make them smaller. I think this should do the trick for both of them. We can also have them a little bit different, so it looks like more like a mummy and a smaller one. So maybe that's kind of cute. And the other issue that we have right now is that they're really the exact same animations, and so I would change the properties a little bit in one of them. So you're doing a delay maybe by 1 second, and you have the baby one maybe move a little faster. So then that should be interesting. It should look interesting. So now they're a little bit different, okay? And baby one, I mean, baby one didn't actually turn out to be a baby one, so let's make it more like a baby one. So now it's definitely a bit small. Oh, I did not do this one, so we should always scale the right way, otherwise, okay, so now what do you think? And obviously, we can move them. In fact, moving wise, I wanted to show you one thing. This is not going to work scale wise because I have this really tiny, I'm going to get a smaller hero marker just so, this is a mummy, okay? And then here, I have a baby, and I put the baby onto this paper stick. And with this paper stick, I could just like, okay, I shouldn't include the other marker, but I now have some flexibility with how I tell a story. So it's like a baby giraffe or something coming to the big giraffe, and could also obviously have them interact. And tracking is still relatively robust. So this is something, these techniques using marker-based and then streaming and all these kinds of things I've explored in my research project 360 Proto, and also in Proto AR, and it's actually pretty cool. You could also do something simpler like cutting out a paper shape like this, but stabilizing is a little harder. I do like our paper stick that I showed you earlier. Anyway, I thought this is cool that you see this. Also, what is interesting now is I can actually also just have it move on paper, but be like more like a Wizard of Oz approach where you can't see me. That's better than me always making my hand visible. So I think this is cooler for prototyping. Obviously you still see the marker, but you get it? It's pretty cool. And then, okay, baby is sad, and then baby kind of like walks away. All right, so that was those kinds of things. I'm going to show you one last thing. There is a cube. Did I prepare a slide for this or did I forget? Nope, there is, I did not have this here, but I'm going to actually add one more example that I have prepared for you, which is the cube, AR cube. So that one I have, it looks like this. I'll show you here. It's a little paper-based, has multiple sides, and so this makes tracking a little bit more robust. And now when I bring in this cube, it actually can track from each of the sides. The C is, okay, now it worked. And so now you can actually move this object. It doesn't always work, but you see how I can now occlude more of the marker? I mean, obviously not always, but it makes tracking more robust. Previously, you could always see like it stopped tracking as it couldn't detect things anymore. It's still not perfect. It's still not the quality that we have in Vuforia with Unity. It is still pretty good for marker tracking. But now, there's always a face of the cube that, that I'm not occluding, and that can be used for marker tracking. And so I can like hold the cube, I can actually play with it more. And I thought that's something I wanted you to see. So AR cube, it's relatively cool little thing on top of ARJS. I think these are all my examples I have for marker-based AR. A few tips at the end. So don't occlude the marker or the marker borders. Smaller markers are harder to detect, look probably better, of course. Size of marker determines the object scale. So I showed this multiple times throughout the view. One thing, if you're working in CodePen or in Glitch, disable auto updating. So in here, you could go to settings and then behavior, and then auto updating preview should be off. Otherwise, every time you type, it's going to reload the scene, which means it's going to reload your webcam, which is annoying to say the least. So disable that. And on Glitch, you just don't use the live coding thing. That's why I always manually refreshed here. And so I think that's the best approach. Going to our ARJS. What's our final ARJS example? What am I leaving here? This giraffe and the baby giraffe. Oops. And that is probably a good way to end the lecture. I'm going to have baby giraffe and big giraffe. I hope you remember these two. And obviously check out the zoo. And you can also work with the opacity settings. Opacity on models is something that will not work initially because A-Frame doesn't implement it. But for example, if you could see this here, it actually mostly occludes the marker because I have opacity 1. So for debugging, I would always reduce opacity so I see where the marker is. Or like the thing that I did is I often show the detected marker in the original pose, so I understand. Like if I didn't show this, I would probably not get why the giraffe looks like this rather than that. I would have expected it to be the orientation a little bit different because of the marker. Original marker, the physical marker, but this is what it was detected virtually, and then on top of this is obviously how the object is going to appear. Use the laptop webcam to develop ARJS interfaces. And so you can work with your laptop webcam. You don't have to have a fancy webcam with ARM like I showed here in the demo. And you could use your phone to show the marker. That is interesting. So that is true. Maybe that's the last thing. Here I'm going to our scene again. Here we have the giraffes. And now if I actually bring in a hero marker, so let me just Google one quickly, hero marker. I don't think it's the best way to do it, but like if you show one in full screen, and when I bring this one into view, I also have the giraffe there. So it's like, okay, I mean, what's the point, right? But I mean, you could use your phone to show the marker. Let's say you're doing a little workshop and you forget to print something, or you want to generate a new marker or something. That could be a use for you to use a display. Could be a screen, could be a phone to show the marker. One last thing maybe. Use browser options to change the webcam that is being used. Yes, so that depends on the browser. When it accesses this the first time, it asks you for permissions, and if it's not the right webcam, then you should go to browser options and check it. Good. So, hope you enjoyed this lecture. It was hands-on, we had a little bit of fun, and I'm going to just wave with my little kanji marker here and hope to see you in the last hands-on one on markerless AR. Welcome to this last hands-on lecture on markerless AR experiences this time. So it's still WebXR, but and again A-Frame, but this time A-Frame, the AR module, and actually some of the latest A-Frame. So using the latest A-Frame master, so that is not actually released yet as a new official release. So some of the things I show you are a little bit experimental. The whole point is we can actually do markerless AR on the web, and so I'll show you what I have here. I previously showed you this markerless AR scene, and so I'm going to play this video, and you've seen this before, but it's essentially my example where I had just a single giraffe here, initially with a 360 preview, but when you go into the AR mode down there, then it uses actually hit testing, so that is one of the more advanced features now, and then you can actually see the giraffe, and it's a life-size giraffe. That kind of fits nicely into the room, and yeah, so I've shown you this video before, and here in this lecture we want to essentially create something like this. So let's look at marker-based AR experiences. I said it's mostly 3D model, maybe animations, light, shadows, maybe menus in HUDs, but then I didn't go too far into that. It's not that popular. If there's interaction explicit, then would probably be cursor-based for marker-based AR. GPS location is definitely, so location is definitely implicit, and then the fiducial, obviously the actual marker that plays a role usually. So when it comes to markerless AR experiences are usually a little richer, but not necessarily in WebXR. I think in WebXR, what we can do for now, what I'm going to show you is 3D model, animation. Yes, I can bring back the animations. I'm going to do that actually. Lights and shadows, I'm going to talk about that a little bit. Environment, yeah, but I mean, I can show you an environment, we can play with that, so let's see how that goes. And physics, yeah, so physics could be interesting, but I think for the current handheld, unless it's physics with a virtual environment, this would work, but physics with like the way I'm going to show it, or the way I've shown it with the HoloLens, using a mixed reality toolkit, where basically the cubes would react to the spatial mesh, that is a little bit too advanced for what you can do right now in WebXR. Spatial sound, that would be no problem at all. Just hard to demonstrate, but it is possible. So hand interactions, yes, if you're talking, obviously if you're talking head-worn. I'm going to show you handheld, but then later, maybe at the end, I'm also quickly going to go onto the HoloLens. It's charging right now, the HoloLens 2. Speech and voice, yes, especially with head-worn, not so much with handheld AR. GPS location, yeah, implicitly, and it's not often used. And then obviously environmental features. Right now, this would just be planes in WebXR. It's harder to get access to the actual spatial mesh. So Depth API was just released on AR Core, so maybe it's going to make it into the browser soon. So first of all, we can actually just take the standard A-frame template, so the one that you see here, and this one. When I run this one on my phone, I'll show you what happens actually. So here is the A-frame template. And I'm going to actually run this in debug mode. That's important. Once I have it in debug mode, did you notice how I now have an AR button down there? So I'm going to go into the AR view, and I'm going to go into landscape. And well, it is actually AR. The way I know is because I can actually move into the scene. So Z is supported, and I can go backwards. And but the stuff is pretty far away, and so it's the sky should be going and all these kinds of things. We're going to make a few changes now. Let's do this first. Hello World is basically like the template, but as I did for the marker based is on the left here. You can see the marker down there. So I removed the sky here as well. And for this one, I'm going to do the same. And I'm going to run the markerless hello. And it is based on this A-frame template. But again, removed the sky and rescaled it down. Just showed you it was too big. So now I'm going to show you this version. And we're going to go to my glitch project, glitch me. And here, if we run Hello World, we're going into AR, then it's kind of like there, it's smaller. And so now it's kind of cooler, right? The distance is better. You can go closer, you can look at the objects, and you can also go further away again. And so basically the sky is removed and I've resized it. I can even make it, want to make it baby size? Okay, let's do baby size. I like baby size, so let's do baby size, just so you see what we can do with the scale. And so this is, okay, now I'm gonna make it really tiny. So I'm gonna make this like that, so that's even smaller, and you can see how small it becomes here. And I still have it at 80 centimeters, and I'm just gonna go over to the phone and run it there. So I'm just gonna maybe get up, edit this. So I'm actually editing this one right now. It is tiny, as you can see, and it's not super tiny. But it's definitely smaller than before. But what I would like is I'm going to make it really tiny. And I think I can also make it a little lower. So it's hard to, it's probably not, it's still above the table a little bit. But I'm going to make it even smaller. So I'm going to go to 2. That should be really, I mean, that's really small. If we preview here, this preview again isn't really great for getting a sense of how big it's going to be in AR, but try this out again. So let's see, I'm going to just reload the scene and small, yes, go into AR. Now it's too low, but it's kind of like floating there now. I don't understand why it is, oh, it went lower because everything is kind of like tiny now, so that makes sense. So I'm gonna actually change it to 1 then, because I really wanted to try one more time. So I'm going into AR, and now this is kind of cool now, and it's floating a little bit above, but it was okay there, that the table is obviously completely monochromatic surface, but it does kind of look pretty cool now. And tracking lost, okay, just because too much white, not enough environmental features. So keep that in mind, right? As you're like going over a monochromatic surface, tracking is terrible. Then it's going to refine itself, kind of like it recovered. And that's why they want you to move left and right initially, and now it's better, but it's trying to it's gonna get confused. So too much white there on my plane, but still, the first part of the demo was pretty cool. All right, so we've done Hello World. Simple, well, simple would just be a, I'm gonna do the simple one. Okay, so simple would just be, we're just going to do a box. I'm going to show you a box that is red. So, and then what I would like to do is we're actually going to have it on the floor, but we are going to have it 50 centimeters in front of us. So if we look at it this way, then yeah, and opacity. We need a little bit of opacity, otherwise it's opaque, obviously. So less opacity, so otherwise it's not transparent. So I like semi-transparent. So I'm going to try this on the phone. So here we go. Reload. Okay, we have our AR box now. And then we move a little bit. And now it is here on the floor. No occlusion, so suspension of disbelief, okay? But kind of looks cool. It's anchored, and I can move above, and it feels like, does it feel like a meter by a meter? Probably feels like a meter by a meter. Yes, so no occlusion here, nothing too advanced, but we should plan for it. It's gonna come. And so that's like one of my tips later. It is going to be there one day. Okay, so we have the box example. We're doing well. We're gonna get the giraffe, okay? So the giraffe is obviously kind of interesting and fun. So giraffe, giraffe, giraffe. So I have prepared this a little bit in my single example. I'm going to get the giraffe. And I'm going to use this as well as my starting point. I will need the Google Poly. So that one I will need, otherwise I won't be able to see my giraffe. And we can always test here, right? And so there's the giraffe now. So we have the giraffe there now. And so that's pretty cool. And I'm going to load it on the phone. The scale that I have here is it's actually the same scale that I used in one of the VR versions. And I'm going to get the animation back because I always like that animation. So I'm going to get the animation from my VR project. I think I had the animation even in basic. Yeah. So here we're going to have that animation. Seems to be recurring, but I just like it and it's cool. Not in this one, it's the one that we're working in. Okay, so if you play this now, then we have a little bit of shaky shaky. Okay, cool. Run it on the phone? Yes. So it's going to be big, okay? It's going to be a big giraffe. So I just want you to be prepared for that. Let's get up. Bam. And then there's our giraffe. And yeah. So it moves a bit. I thought it moves a bit. Yeah, it does move a bit. Obviously the entire body moves, but it is pretty cool. So we have the giraffe in here. And one thing that I wanted to talk about is that we should definitely do a little bit more about light. So what you can see is obviously I have a light source over there. And so obviously from this right side there should be light. But from this left side, there shouldn't be light. There is no light source, nothing is on this side. So I'm gonna do a little bit about the light. We don't have light estimation at this stage, but I wanted to do something about the light. So this is my demo here. We're moving a little faster than in some of the other demos previously, but we already know more now, so that's why we're faster. So what I want to accomplish is a spotlight on this side, and I also want to reduce the ambient light a little bit. So I'm going to do this in 2 steps. I'm going to actually have, I'm going to add an ambient light. So a light type ambient, and then color can be silver, and so that's my light, and intensity should be maybe 7. So let's see what that looks like. You can see how it's already darker. Okay. But we will have a light coming from the right. So I'm going to actually add that light from the right now. I'm going to use the spotlight again. I mean, we've done this kind of before. And so I spot. I'm going to make it pretty bright. Intensity. Yeah, I have a pretty... so the position is interesting. So I know, so what I'm thinking is the giraffe is at 0, 0, and then 1 meter in front of the camera. And I'm going to place it roughly where it was before. So I know that my light source is a little bit off to the right from that giraffe. Same, actually, this is maybe 1.8 meters high, the source, and maybe 1 line. And so I'm looking like at the light source right now, and then also roughly a little bit further back, so it's a little bit, I wanted to, and then we actually wanted to shine at the giraffe, so we're going to say giraffe is our target. So now we're getting a light source from the right and there. And actually what I'm going to do is, for debugging purposes, I'm going to put a little sphere in there. We're going to make it color FFF, so also white. We're going to make it, it's going to be right where the light is, and we're going to have the scale a little bit smaller, so maybe, so I want it to be looking like a light bulb, and opacity, because it's for debugging, so relatively low opacity. I just want to show you where the light source is. So this is roughly where I've placed the light source. Let's make it yellow, even though our light is not yellow, but just so for debugging purposes. So what I'm starting to do here now is show a little bit how I can play with also light in AR when I don't have light estimation right now. So we're going to run it. So I've defined a spotlight, it's shining at my object, and I placed it roughly where I believe the lights are. So going to reload our giraffe here, and there is, we can't go to the right yet, so I'm just going to get up and I'm going to place it in AR roughly so where it was before. So now it's there. And let's see, so the light source, hey, I did pretty well, right? The light source actually matches that one. And I'm gonna just make sure that my leash is long enough here. What do you think? I think it's cool. I kind of matched the light source, and it's realistic that it gets lights from this side, and it still looks kind of cool, and it's moving. And here we have, oops, cable. I need to make sure that I get the cable with me. 1 second. It does really look cool, doesn't it? Okay, so, and now with the cable, we are going to this side, and it's still relatively bright on this side, but it's not as bright as on the other side. I'm just gonna look at the giraffe. And yeah, I mean, obviously this is a really shiny giraffe, but I like it. It's pretty cool. I can look up at it. Wished I could feed it. Now this is sad that we don't have people segmentation. Obviously it would be great to see my hand in front of the giraffe. So this is something that is currently not possible. You know, in my VR demo I threw like things on the floor to feed it. We could actually drop something on the floor. Oops, a little bit of a tracking issue. But anyway, I'm pretty happy. And also let's just look at the light. I did a good job there. Kind of like matched it really nicely where the light is. And tracking works, well, okay, just when I said it. But still cool. So, we did our giraffe example and we placed it in the environment. And the last thing I want to show you is hit testing. So for that one, I'm gonna actually, it's a little bit more advanced, so I can't run it in CodePen, and I have everything prepared here in this file, and I'm using a contribution, and I should acknowledge this, which I thought was pretty cool, a contribution from this project. This is the original hit test project, and I've edited it and adapted it. And this one was created by Ada Rose Cannon, at least that's the nickname here. And it's a cool little example. So in her example, there is a lion, and she has like this lion. They have this lion, and yeah. We are going to first just have a cube because I want to show you a few things. So I'm going to go into my hit test example. So I'm basically getting that hit testing library. Since it's experimental, I have to use like the latest build, or one of the latest A-frame builds. So it's not the release yet. And then I need to use WebXR optional features. So this is from the WebXR specification. So the latest A-frame master supports the WebXR property on the A scene and uses some of the WebXR stuff that is now in Three.js or directly in the WebXR specification through the browser. So they added it. I think these things will merge eventually and become quite cool. But for now, we have to use hit testing. And hit testing is when you, I'll show you in a second, but when you basically look at the screen and touch the screen, and then it finds, from your touch point, it finds the plane that touch point would intersect with as it shoots a ray into the scene. So we've talked about this in the lecture. And good. I'm just going to have a box there. So I also have put it on a plane, but I hide it in AR. That's something that Ada provides, and so I just use that as well. And this world, which is kind of like a preview, so when I run it in here, I'm just gonna run the hit test now. So hit test. So when I run it, you see it like this, and I will replace the whole thing with it in AR. And for that, I have a reticle, and in that reticle, I have a preview of the box. That's how I've implemented it. It's basically the same thing that's going to be placed in the world, but it has lower opacity. And I should also do shader flat. Yes. And although I'm not sure exactly whether that's going to work with the opacity. Anyway, so we'll see. I'm going to run it, okay? So time to run it in on the phone, so in AR. So this is now with hit testing. So clearly more advanced and close to what I showed you with the giraffe earlier. So here we have the AR version hit testing, and so now I'm gonna actually start it. So when I started in AR, then it shows this preview where the cube is gonna be. So if I'm gonna go here on this white thing, then it's gonna be sitting, it's actually still on the floor. It didn't really detect the plane. But okay, we're placing it on the floor. So me moving the phone up and down actually does a hit test and places it at the hit test location. And when I press, it actually really places it there. And here I can also put it up on the screen. So now it's like sitting, sitting on that table. So we're gonna put it here on the chair. So I like these previews. I think it's better than some other form of reticle. I'm going to show you a more primitive version. Could be we just show a ring there, a ring, and then material shader flat, and rotation is I'm going to put it flat on the floor. So color. We're going to do white, and opacity 0.9. So I'm going to just like have this as a preview, put it on the world. So that's the way you can debug things. So it would show me this ring, and then it would place the cube inside. So that's cool, but I don't want to see that in the initial view, so only after placement. So let's see what you think of this. Let's gonna run it, gonna get up without killing everything. Okay, so reload, go into AR mode, and as we move, we see a pretty big reticle. I think it's way too big. So I'm gonna actually change this, okay? I'm gonna make the scale, forgot the scale. Scale is important, so we can really work with just a much smaller So just 15% of this will do the trick. Let's go back, try it out again. I like, it's not really preview, right? It's more like telling you where the placement would be. What do you think? So standard reticle, and then you would, yeah, okay, we get the idea. And so it would like work like this now, or place it here on the chair. Can we place it on the chair? It's going to be on the floor. It didn't detect the chair surface yet. Okay, now it got it. So now we placed it on the chair. So, okay, so that's the reticle solution. And this is nice. I put it nicely on the table. So this is hit testing. As I touch, it actually then places it at where the intersection is. It does actually constant hit testing all the time. That's how it finds planes, and then it puts the reticle and adapts it to the size of the plane. So kind of like it rescales depending on how big the plane is. So that's similar to, at least in this implementation, to marker-based tracking. These were my demos. I'm going to wrap up here with a few tips and tricks. A lot of this stuff is pretty early stage. And wait, I wanted to show HoloLens. I'm going to do HoloLens. Do the GoPro. Okay, so I'm going to just go into the browser, Edge. So I can place it here. Okay, I have already entered the URL. I'm just gonna load it one more time. And so then there's a little warning there. I don't know why that is. So it's just like a little bug there, I guess. So here we have already the scene, and we can interact with it a little bit. But I actually want to go into the VR mode and place it. It's going to be there. So I could have placed it a little bit differently, I guess. So anyway, so it is here now. And as I get up, you can see how it's kind of like, obviously none of the occlusion stuff, nothing advanced, even here on the HoloLens, not working. But it is cool, so we can see the scene, and yeah, so it appears larger than what I thought we had. Let's just double check the code one more time. I'm gonna actually lift this up so that I can edit this. So we would want to make it even smaller, and so then I'm gonna make it actually 0.5. That would be larger actually. So 0.05. Let's see, that should be quite a bit smaller. And I want to make it really 1.2 high. So, oops, I didn't adapt one, so this is wrong. So now it's tiny. Okay, let's see what this looks like on the HoloLens. So let's go in here again. How do we, so go to home. This closes this, all right. And I'm gonna activate this, so it's gonna follow me, and I'm gonna kind of like place it here in roughly more like in front of me. So I'm gonna leave it here, and I'm gonna reload the scene. Okay, and I have changed a little bit the resolution. It's definitely tiny now. You can see how small it is, and I'm gonna go into VR. Well, actually, I'm gonna go into AR. So for that, I actually had to enable some of the web VR settings. And now the question is, where is it? Oh, it is really here. I didn't even see it. Now that is cute, right? So that is a tiny little A-frame scene. Yeah. Okay. Cool. So it does work with macOS AR. It's really tiny now. I don't know. I've always, yeah, that's what I was looking for before. It's so cute. Okay. We are done here, and that's the HoloLens part at least. So Okay, let's take this off then. All right. So I'm going to show you more WebXR samples. Let's do that. So let's try to find them. WebXR samples. Good. Samples. There's an AR stuff down there. Positional audio. Hit test. Hit test API. AR basics here. Hit test. That's the radical. That's the flower. Bare bones AR. Extremely simple. Which one is cool? So let's do no dependencies. Okay, let's see. Hit testing. Start AR. This one has their radical, and then it like places flowers there, sunflowers. Yeah, pretty nice, right? I know. It's always nice to have a little bit of a model, but I like my giraffe. Okay, you have a few flowers. Immersive AR is the planets. I always like solar systems, so this is cool. Let's go into landscape, and now we have all these planets here in my, well, this one here even, huh? And then there's the sun. Wow, their sun is big. My version of the solar system wasn't so bad. Check it out in course 2. Course 2, everybody. Okay, so more WebXR samples, if you will. Good. So now we're going to wrap up. So tips and tricks. Provide a preview of the content during placement. I wanted to show this with my cube. Essentially, it's relatively simple, but you could imagine like some kind of simplified, maybe a little bit reduced opacity, so more transparent preview, so that I know actually what the scale is going to be once I place it. Because what I don't like in a lot of the experiences right now, I always have to place it first, and I have no idea what's going to happen. It's always like a surprise, and probably not a good idea. The other thing I say here is incorporate light and shadow to blend with the environment. That's my example with the giraffe. So here, this one, where I then started to place a light in the background. I thought that, which is then here on this side, place the light roughly there, and then a spotlight to shine on this side and make it a little bit darker on the other side. Also, you could see initially it was too bright for the room, and so reducing the opacity with the ambient light, the light with the ambient light, with the shining a little bit darker, less intense ambient light was already an improvement, I would say. So plan for that, and also plan for the impact of occlusion rendering and light estimation. So very important. If you don't define lights, it'll just be the default lights, and I could imagine that as soon as the light estimation stuff is more or less available per default, we don't know actually what the good default would be, but it might be that it actually really then reduces the light for your entire scene. In my case, it would obviously be great to, rather than me hard code, I know where the light is and I know relative to the giraffe because I knew where I wanted to place the giraffe, but rather than hard code it this way, it would be better to obviously have light estimation. And light estimation would give me the temperature and the color of the light roughly at where I'm pointing probably. And I'm not sure whether they're going to ever be able to estimate the location of the light, the source. They obviously, when I bring it into view, they may remember. We can build a history, and then we can see there was really a bright temperature and color there. So I use daylight bulbs. That maybe makes a difference as well. And also occlusion rendering. So as soon as that kicks in the browser, you should think about what that means in terms of scale for your experience. And this is what I also would say as tips and tricks. I haven't shown that too much here, but I would prototype these marker-less AR experiences using 360, VR, or marker-based AR. So I have this example here with the menu and this is my menu. Where is I have this 360 example here. That's what I mean. So with the 360 example, what I could do is I'm going to just grab the 360 here quickly, and for one of my examples, so here was the giraffe, with the light, with the ambient light. So now I'm gonna just like bring in, I don't need this, but this image, and I'm gonna have a sky that I just do for testing, and I'm gonna use the photo. And so if I now test it this way, I basically can preview. So in 360, I'm going to reload again. So now in 360, I know roughly, okay, at this stage I had the glass table a little bit closer to where I'm sitting right now. But the light, I kind of like matched relatively well. And I was doing this relative to the giraffe. But with 360, you could prototype before, like even without being in this room, I could start a prototype. I know roughly, okay, I'm going to start here. That's my starting location. So from there, the giraffe is going to be 1 meter in front. And then the light is going to be 1.2 meters to the right and 1.9 meters high. So that's how I was, that was my approach here. And so you could also use marker-based AR. So I've shown you all these examples before, like here with the giraffe, marker-based, previous video. Obviously then from here to there, we can change the scale entirely. With marker, unless I place a really fat one on the wall or on the display in the background, it would be hard to have the marker needs to stay in view. So it would be hard to get an experience like this where you're really looking at a life-size animal with a marker. But anyway, could prototype it this way. That's all I'm saying. And then consider allowing users to adapt the scale of the experience, right? Right now, it seems like something with the hit test example that I was using and that was kindly provided by Ada, so someone from the community, the WebXR community. With that, I mean, we can adapt the scale according to kind of like the plane that we're detecting, but not really, we're still making decisions on behalf of the user, and maybe we should actually ask the user or indicate like the scale of their experience. Obviously I could point, I mean, I have a little bit of control, right? I can point at the different planes and I can see like on the table as I had it, or like here on the glass table. But we could still give users more control, I feel like. And then also finally consider adapting the layout to fit the detected plane. So example would be when I look at the table here, like I could actually lay out the scene maybe this way, and then when I place the giraffe in the room, maybe in this view, the layout could be more so longer or deeper, let's say deeper rather than wide, and so more along the Z. And so what you didn't see so well, but as I was moving around with the reticle, the orientation of the animal actually was kind of fixed. So we can show that here in this example. I'm going to come back to this video. So here, when I go into AR, what I showed initially, you see how the orientation is fixed. So that is essentially the reticle that I'm using here, and that orientation is always fixed. So I cannot actually place the giraffe in a different way unless I restart the app. And that's something that I think we should definitely address somehow, because that is tedious. It looks cool in initial demos, but the more you think about these, it's still experimental, it's still early stage, and it's not the final experience yet that we would want for our users. But so these are my tips. So consider adapting the layout to fit the detected plane. And at this stage, I have to say it like consider and maybe perhaps do these kinds of things, just because it's so experimental. Unfortunately, at this stage, it's not. It's like light estimation, occlusion. That's all going to come very quickly to the web. Might already be there. I mean, we are in September 2020 right now, and so maybe when you watch this, it is there. And at that stage, I feel like I should do an update of this one. Also, by the way, if you enjoy these kind of like more hands-on lectures, I've often done online office hours this way with students. I fixed their code live, and others could learn that way. And I would be prepared to do something as part of the MOOC as well. So let's see how we could schedule this. Obviously with time zones it's going to be difficult. But I enjoy, I don't mind making mistakes and then learning, and then have you learn with me that way. So I think that would be a great way to learn. So I enjoyed these 4 lectures that were a little bit more hands-on, and a lot of things went wrong. But so hope that you still learned something. They're also a little longer, but less edited, and I think that's actually probably good. So you can maybe follow along, or at least like try to follow what I'm doing. So each of the examples, by the way, that I had here, they have links. So hello world, and I have them all. This is obviously my code pen. I have them all in this XRMOOC project that I'm gonna actually give out with the MOOC, so that you could have a starting point. And I will also update this from time to time when I have the time. But I'll promise I'll keep it up to date. I'm obviously working in this space, and my students in the residential program also need the latest code bases, so there are strong incentives to keep this up to date. So thanks for watching. Hope you enjoyed it. So now keep working on your AR scenes as part of the honors track. Hopefully that's why you're watching this, so that you can get a better understanding of how to approach that step. And it's exciting. And then get ready for the peer review. So also watch my instructions there. Hope to see you at the end. Also hope to meet you at some stage in person, obviously, or at least in some kind of online office hour world. All right. Thanks for watching this. In this video, I'm going to give an overview and an introduction to our augmented reality scene exercise. So this is the exercise where you take your previous 3D scene or virtual reality scene, which I hope you have completed at this stage, and actually create augmented reality versions of those scenes. You just have to do one of them, and but we have so many options. So you could go for a ARGS marker-based approach, so using A-Frame. You could go for Unity and use Vuforia and use some of these markers. You could design your own markers and create a nice marker-based experience. You can also, if you have an AR Core enabled phone, like this is the Pixel 4, then you could you could do markerless. If you feel like you want to do head-worn AR, that's a possibility as part of the exercise. You could do it in many different ways. So obviously, if you do have access to a device like the HoloLens 2, and that's pretty cool, that would make it, well, that would mean that Unity and Unreal are really good development environments for the HoloLens. So I would say that would be a way to go. If you are staying with web-based, so you can do, so WebXR, you could do HoloKit. So this is the phone goes inside there. It's like a cardboard. So an AR cardboard, if you will. So phone goes in there, and camera needs to be exposed in order to do marker tracking or do markerless AR. And in this case, you would view it like this, and you need to do a stereoscopic rendering. Now that is the tricky part. In A-Frame, for example, the way to distinguish between AR and VR is stereoscopic view and AR is just normal view, and then 360 would work. If you wanted to really use the HoloKit or the cardboard, you could also use cardboard. You could use the cardboard and cut out a portion so that the camera is exposed. There are cardboards where the camera is already exposed. In this case, I have to make sure that it's kind of like this. I cut this out for a different phone, I believe, and so I would have to adapt this a little further. It's important that the camera is exposed, as I say, because you want to do augmented reality, and so you're basically showing on the screen the camera feed, so that gives you kind of like a see-through that turns it into glasses, if you will. Obviously, because of where the camera is positioned, you have a little bit of an offset, and so you will notice that as you walk around with something like this. I do have code where we can render an A-frame scene for each eye and therefore do a stereoscopic view as a basis for AR as well. So I will share this. And it's not really how A-frame is designed, but it's possible. So that means we can really approach this exercise and do it with any of the platforms that we have, that we are targeting with this MOOC. So WebXR, Unity, or Unreal. And you can do both handheld AR, so with a smartphone, or a tablet, like an iPad, and or head-worn AR. So lots of possibilities. I'll go over the specifics of the exercise in terms of a task description. So your AR scene, create an AR scene in A-Frame or Unity or Unreal. So please use one of these platforms and tools. A-Frame is our tool of choice for WebXR. Keep it to WebXR, Unity, or Unreal. That way, we're making sure that we're all learning similar things and can help each other as well. Your first step would be to add an AR module or plugin. And a lot of these, in Unity and Unreal, you have to make sure that you have to write plugins installed and have them activated. In A-Frame, it depends. If you're doing marker-based AR, you would have to add the ARJS module, if that's how you think about it, or it's an additional library that you have to add. And that way you get access to an AR camera and then maybe an AR session. So that's how this usually works. And then you should be able to view it in AR. So if you're using marker-based AR, that means you can just stick to a webcam that you have connected to your computer or laptop and do it this way. So it would usually just mean that you hold up, in Vuforia, for example, you would hold up the marker to this camera. And I've shown examples of this. The other way to go about it is for example, using ARJS. You could develop against the computer here, and then then run it on your phone very easy. Just like use CodePen or Glitch and run it on the phone. Go to the correct glitch.me URL or to the CodePen debug view. That's important. So you have a full screen view of the scene, and then you can bring the marker into the view of the phone, and then you would have the AR experience. So that would be marker-based, and markerless, obviously, no markers. So that would be the task. So you adapt the 3D scene that you had, or VR scene, depending on which you choose as a starting point, for AR. So that usually means you're probably going to play around with scale, maybe with layout, making sure that when you have objects, for example, you're designing relative to a marker like this, you need to print this out, you choose the size of the marker, and then obviously this is your unit. So marker size is 1 in A-Frame. So scale 111 would just fit right on top of this marker, as I've shown in the lecture. So you pay attention to these things. You need to keep the marker in view. So if I do it like this, it's obviously not going to be recognized. So I did these little pockets at the back of my paper so I can hold it up nicely to the camera. Or I can also place it on a wall, like, I don't know, tape it, or just put it down, flat. So we can do all these things and then bring the phone in, and then we have an AR experience. So you may need to adapt it further because you definitely need to keep the marker in view. For markerless AR, you don't have to worry so much about it. Then in the next step, I want you to actually think more about how could this fit in better, blend more with the environment? So make it more an augmentation rather than something that really stands out. We want to make sure that it fades in nicely, it blends in nicely with the environment. In some tools, you may have object blending, so that does some kind of occlusion rendering for free, or removes, fades out part of the object as a form of occlusion, but it's a little bit different. So the WebXR model viewer version, for example, is a good example that shows you that. I don't think it's the tool that we should be using here. I think you want to go beyond that. So I didn't suggest that you should use model viewer. So you want to play with the light. And another way that I want you to think about is another way to make objects fit in with the environment is by thinking about sound, adding sound, spatial sound. That is a nice way of transitioning. Think how they think about how they for example, do cuts in a movie. They often play the voice of the actor already before they show the actor, and that is a nice transition. And this principle, in some sense, allows you to do a nice blending. And that's something you could play around with. You could pick up some environmental sounds and also add them to your AR experience. Obviously, you can come up with new sounds as well. Think about background sounds to blend this more. If the idea is to turn this here into a zoo, which we did, then just having a little bit of background, rainforest or whatever, I think we chose rainforest sound. They gave us some nice bird sound. That changed the experience completely. And I don't know, it made it more believable. It didn't change much visually, obviously, when I did the AR version. I'm going to show you this. But just having that sound in the background really made a little bit of a difference. So consider that. And optionally, make the 3D objects interactable. I mean, so I'm saying fuse, tap, drag, etc. So that would be mobile phone based. Fuse would be like if you're having if you add a cursor to your scene and then you dwell on an object and then you would fuse. So basically, if you're using a cardboard somehow like cut out and the phone inside, and you're using it in an AR fashion, then you could still use a cursor like this. You do have on the HoloLens, and on the HoloLens 1, you kind of like tap where the action is triggered where you're looking. So you're using gaze, your head gaze, not eye gaze, head gaze, to determine where you're clicking, and then you're just activating that gesture. Now, in some sense, you could do this. You could save the $3,000 whatever dollars it is for the HoloLens and just do it with cardboard. It's not going to be the same experience, trust me. But you have a button here, and you can simulate something like this, so that one day you may deploy it to the HoloLens 1. HoloLens 2, which I have here, is obviously a different story. It has fully articulated finger and hand tracking, actually 2 hands, no problem. And you don't actually really have a cursor. Usually in front you have cursors at the end points of the rays coming out of your hands. So the interaction modalities and the interaction techniques differ quite a bit between devices in AR. But you can work on this exercise and you can make it a head-one AR solution if you want, even with the cardboard, or if not the HoloKit. So this guy, so you have flexibility. I'll provide some links to some of these if they are still available. The HoloKit was sold out recently. So I'll try another approach. So that will be the 5th step here. And I think if you have the equipment, so let's say you've started marker-based and you have the equipment, so that means you can do markerless AR, I would like you to try this out. Even if you have a more advanced, so AR Core or ARKit capable smartphone, let's say, you would learn a lot from transforming this markerless approach into a marker-based approach, just like we did in our case study. I'll come back to that in a second. So the expected results of this exercise would be that you actually have a better sense of scale and perspective now in AR, so that's different from VR, that you create this AR experience in layers. So you're thinking about form and background, but you're thinking about that a little bit differently. So in VR, I almost said the same things, but form, mid, and background here means really aspects of the environment that you want to blend with. So this room around me, think about what is in the foreground in this room really depends on your location, obviously, so in wherever you're trying the AR experience. And so think about how do you want to blend in, and think about the color, the distance, okay? So this room is, for example, not very big, and so you should really pay attention to dimensions. So if you put, like if you're in this room and you're putting an object 5 meters away, that would mean it's like outside this room. And that's what you saw in my first steps when I was first running it with AR Foundation and I placed the object further away. It didn't feel right. The Burton Memorial Tower seemed to wasn't in the room with me. Now I didn't have occlusion rendering, so I couldn't tell, like the walls, it should have been occluded by the walls, but that AR Foundation, the way I deployed it didn't have that. And so you adjust the scale so that you bring the objects closer to you, and that's something that you will have to play around with. So scale and layers, and also then supporting interactions. And the way interactions work is different in marker-based and marker-less AR. So also depends on form factor, as I said, whether you're wearing the device or holding the device, or handheld versus head-worn. And that's something I discussed in more detail in my lecture, so please refer to some of the information there. And I'm going to just go over, bring back this. And here we have the marker-based version. So I'm just going to go a little closer. So that sound is important, that you can hear that sound initially, that sets the atmosphere, that actually determines that I feel like, okay, that is a big aspect of making me feel like I'm looking at animals in a zoo. And then otherwise it's a marker-based AR experience. And what you see here is obviously I brought back the case study and I adapted parts of it from VR to AR, so it is possible. I had to play a lot with scale. I did get rid of some of the animals or remove the environment. Obviously no need for controllers, no teleportation scripts, nothing like that. So I could simplify quite a bit. But even then I had to pay attention to performance. So environment has to go. Running a video feed the whole time on older phones is going to make them warm. At some stage they're going to throttle, they're going to get too hot, and then the performance goes down. I hope you don't have to observe this. It's not going to explode or anything, but performance is going to be really bad. And here we have a marker-less version of the zoo. And that's something I showed in the lecture, so in a bit more detail, but obviously it's pretty cool. Running an experience marker-less gives you a lot of flexibility. So here I'll just like go down there and visit the animals that are now living on my carpet. And it's cute with animals. Maybe it wouldn't be so cool if you had other content. But in the zoo case, it worked pretty well. And so I was just playing around. As I was shooting this scene, I was wondering, what's the best way to fit this, blend this into blend it in with the environment. And I tried tabletop AR, and even with markerless, and then it didn't feel right. And so I went down on the carpet, and I thought it was pretty cool. And that's where I would like my users to experience the zoo, and that's how I did it. But obviously, it would be totally fine if you took a smaller scale, so smaller scope actually. And here I'm showing you just one animal in AR with a marker. You've seen this before, so this is something that I think would be a great start, and then you can start exploring how you want to present it. Maybe you can even hide the marker, so I could actually put a white plane on top. I just have this really nice white surface here, so I could hide the marker rather than actually show the digital rendering of the marker. That was just for debugging purposes. And so here I'm going to show you the marker-less AR version. This part is just 360, okay? So this is just using the gyroscope and accelerometer. So you have to go into the AR mode in A-frame. I'll show you that. And then in this case, we can place, so we're choosing a place where we do some hit testing to figure out where we want to put the object, and then it's in there. And now, since it's marker-less, I don't have to keep any marker in view. Sometimes you do see some issues with tracking, just like now it shifted. And that's something that happens sometimes, especially as you hold up the device or go in areas that are not as well lit. Hold up the device against vertical surfaces, and you can see how, at least in this room that I'm using here, the walls are just very monotone. There's not much on the walls. I cleared it a little bit out. So the more you have on the walls, the easier, the more robust the tracking will be, the more features can be detected. So that's something to keep in mind. So as I was talking about VR experiences and content and interactions that go into VR experiences, as I said, when it comes to immersive, you almost fill all this out. And then obviously explicit interactions, you do a lot of controller or hand-based interactions, and then maybe speech and voice. So how does it look for marker-based AR? So marker-based AR, I think those experiences are usually simpler. So you do see 3D models, maybe animations, lights and shadows, yes. Maybe some kind of heads-up display. Usually not so much about menus. Most marker-based AR experiences use a cursor, so that is easier for interactions, at least the A-frame ones, let's say. You do have issues with clicking. I'll show you this. It doesn't work as well. There's an issue in deep down in ARJS. I talked to the developers, so that's something we'll figure out. We can actually just work around. We cannot fix it. So I would recommend you using the cursor for a marker-based AR experience. So really putting reticle in the front, and then in the front of the user, and that's like the gaze that they would use to interact with objects, similar to how this is done on HoloLens 1. And then you support implicit interactions. You could use location, obviously, like where you are. You don't actually have to use explicit GPS location, but it is done often by marker-based experiences. You could use time of day as a variable to determine whether the scene should be dark or not. That would be interesting how it blends in with the environment. With some of the markerless frameworks, we can do more. We can actually do light estimation. Obviously, you need a fiducial, so you can do the predefined one. So when you're doing like an ARJS one, make sure you're using a decent size. Make sure that you're cutting it out, leaving some white gaps around it so you can hold it. This black border is significant, is important. The Vuforia markers with Unity are much more, let's say, robust. So you can hold it like this. It would still be, well, that might be a little tricky now, but you can occlude a significant portion of this marker and it would still be detected. Issues in my examples are the light conditions here that are optimized for video so you can see me well, but they don't work very well when I'm actually using marker-based AR. There's a lot of reflection on the paper, and that then makes it hard for the camera to detect anything, so that's something to play around with. I have more tips on marker-based and markerless AR with WebXR, so please look at those lectures if you feel like that's the way you want to go. For Vuforia and Unity, it's relatively straightforward. And you could also do random marker generators, or you could also do your own custom ones if you add them to the image database in Vuforia. In Unreal, I haven't done marker-based AR in Unreal. I don't know how it's possible. I don't know that Vuforia works with Unreal. Last time I checked, it did not. So I don't think that's an option. So if you're doing Unreal, then you're going markerless. That means AR Core and AR Kit or the HoloLens if you have that. Or obviously Magic Leap or Nreal or whatever other AR device might be available. Apple Glass maybe. So that would be interesting. Although it's unlikely that it'll work with Unreal. So given the current situation. So here let's talk about markerless AR. So 3D models and lights and overall a much more complex environment. And in fact, you have light estimation. So you would normally use environmental features. So I mean, both the geometry, so spatial mesh or mapping, maybe even the semantic layer. So whether or not you're looking at a chair or a window, you can do in some of the, so in ARKit, you can do this relatively seamlessly. AR Core is adding support for semantic classification. So that should be available maybe when you're trying this. And then on HoloLens, you also already have scene classification. So you could do that. And then physics, I think, is pretty standard with markerless AR. So my cubes example on the HoloLens, I just throw cubes on the spatial mesh, and then they kind of like bounce off in the, and it matches nicely with what happens in the physical, in the virtual. So it maps nicely from the virtual to the physical environment, and so it feels like I'm throwing cubes into my studio here. Spatial sound is a good way to make it a more believable AR and markerless AR experience. You would probably do something around hand tracking or touch screen, so gesture. Speech and voice is something that becomes more and more popular, especially head-worn. AR and smartphone, so markerless AR on a smartphone, you don't see a lot of speech and voice on handheld, but markerless and head-worn you do. It's interesting. And these things may shift a little bit, but this is my current analysis. And so this brings me to the end of the introduction. Essentially, this is the beginning, right? This is not the end. This is the beginning of the exercise. So I hope you learn a lot. There's a lot of options you have in there. We had to keep it very flexible. This is a very quickly moving space. Most of the information I just provided should still be accurate. Maybe there is a new update to A-Frame or Unity and Unreal, but I mean, you can refer to my marker-based and markerless AR experiences lectures. I'll go over the main steps. Please refer to the first steps in each of the platforms. I show how to go from 3D to VR to AR, all in one video for each of the platforms. So that should be your starting point. And then finally, please talk to each other and help each other out. Use the forums, submit things in the galleries if you have issues. As a last resort, you can obviously also reach out to the course operations team that finally, eventually, probably will get hold of me, and I should also be able to provide some input. I'd be curious to know if there's something really going wrong, but we have done these exercises for a while now in my classes, and yeah. So obviously, this is not a step-by-step exercise. This is how you create a marker-based AR experience with this tool. No, that's on you to do this. I guide you through the process. I think if you follow my approach, which is relatively universal, it goes across all the platforms. It works in the same fashion, just the tools are slightly different. You will actually get really good at developing AR experiences. There's many more advanced things on top of that. So overall, in the grand scheme of things, this is still introductory. But I think you should feel very proud if you get to seeing things in AR, be it marker-based or markerless. That is really not a big deal. I do think you would learn the most by trying out both if you have access to these technologies. So good luck. And don't forget the peer review. I'll also introduce you to the peer review and how that would work. And you're almost there. You've almost, at this point, completed the honors track in this course. That is a really great achievement. This is the technical course that we have here, and not too much step-by-step guidance. You have to fill in a lot of the gaps, and I appreciate it. I do think that you learn a lot by doing these things yourself and looking up things. You'll become a much more independent developer that way. If you're getting lost along the way, again, don't hesitate to reach out. Don't reach out. I'm sorry. Don't reach out. Don't ask me. No, you should. You should ask your peers. That's the number one address. And then if you're all stuck, then I'll try to help us move forward. But I've seen good success among my students, so I think you'll manage. And I'll see you in the peer review at some stage, hopefully.